What if you could witness the very dawn of time? Picture a cosmos so young, not a single star yet glimmers in the profound, silent darkness. This was our universe, over 13 billion years ago. A vast, empty canvas waiting for the first brushstroke of light. It's a realm we can scarcely imagine. A chapter in the cosmic story that remains one of the most profound and tantalizing frontiers in all of science. We live in a universe ablaze with galaxies, each containing billions of suns, but every one of those brilliant lights had to start somewhere. They all trace their lineage back to a mysterious epoch when the very first stars ignited, ending the cosmic dark ages and setting the stage for everything that would follow. This is not just ancient history, it's the story of our own origins. The iron in your blood, the calcium in your bones, the very air you breathe. It was all forged in the hearts of those long-dead, primordial giants. We are, quite literally, made of stardust, and to understand where we come from, we must journey back to the beginning and confront the enigmas of creation itself. This journey into the deepest past is what we're embarking on together today. We're going to peel back the layers of time and explore 30 of the greatest mysteries surrounding the first stars and galaxies. These are the puzzles that keep astronomers awake at night, the questions that push our most powerful telescopes to their absolute limits. How did something emerge from almost nothing? What did the very first star look like, and how did it live and die? How did these earliest stellar furnaces gather together to form the first fragile galactic structures? The answers are hidden behind a veil of unimaginable distance and time. But with every new observation, every cutting-edge simulation, we are gathering clues. We are cosmic detectives, piecing together a crime scene that spans the entire observable universe. So, get ready for an adventure. We're about to dive into a world of dark matter halos, supermassive black hole seeds, and cataclysmic supernova that could tear a star apart from the inside out. This is a story of extreme physics and breathtaking beauty. A narrative written in the faint, ancient light that has been traveling for billions of years to reach our eyes. It's a fun, mind-bending, and utterly fascinating exploration of the universe's wild and chaotic infancy. From the formation of the very first spark to the assembly of the earliest cities of stars, we will uncover the secrets that challenge our fundamental understanding of reality. This is the epic quest to find our cosmic roots, and you have a front row seat. Our first great mystery takes us to the very foundation of the cosmic story, to the stars that started it all. Astronomers call them population 3 stars, and they were fundamentally different from anything we see in the night sky today. Our own sun is a population 1 star, rich with heavy elements like carbon, oxygen, and iron, the very stuff of planets and life. But in the very beginning, the universe contained only the primitive elements forged in the Big Bang: hydrogen, helium, and a tiny trace of lithium. There was no silicon for rocks, no oxygen for water, no carbon for life. The first stars had to build themselves from this sparse, elementary material, and that purity had profound consequences. Without heavier elements to help cool the primordial gas clouds, the process of star formation was far more straightforward, and in a way, far more brutal. These clouds could collapse into much larger, denser clumps than what is possible now. The prevailing theory suggests that the first stars weren't just large. They were titans, behemoths that could have been hundreds of times more massive than our sun. Think of a single star so brilliant that it outshone an entire modern galaxy of stars, a lone lighthouse in an ocean of darkness. Its surface would have been blisteringly hot, radiating a fierce, blue-white light unlike any color we know, and its nuclear furnace would have burned at a ferocious, unsustainable rate. This incredible size dictated a tragically short and dramatic life. While a star like our sun will burn steadily for billions of years, a population 3 giant might have lived for only a couple of million years, a mere cosmic blink of an eye. Their deaths were as spectacular as their births. For the very largest of these giants, their end did not come as a typical supernova. Instead, they may have succumbed to something even more extreme, a pair instability supernova. In its final moments, the core of the star becomes so intensely hot that the energy itself begins to spontaneously create pairs of electrons and their antimatter counterparts, positrons. This process robs the core of the outward pressure that was holding the star up, causing a catastrophic collapse that triggers a runaway thermonuclear explosion. The star wouldn't just die. It would be utterly obliterated, completely torn apart from the inside out, leaving no black hole or neutron star behind. It was a self-destruction of such magnitude that it would have scattered its uniquely pure, heavy elements far and wide, seeding the cosmos for the next generation of stars. And this brings us to the heart of the mystery. We have never actually seen one. Every single thing we think we know about population 3 stars is based on sophisticated theoretical models and computer simulations. They are, for now, ghost stars, brilliant, fundamental, yet entirely hypothetical. The central problem is their unique chemical fingerprint. Because they were made of only hydrogen and helium, the heavy elements they forged and then spewed out in their supernova would have a distinct chemical signature, one devoid of the pollution from earlier stellar generations. Finding that pristine signature in the light from the most distant quasars or the faintest, oldest galaxies is the holy grail of this field. It's like trying to find a single, specific grain of sand on a beach that spans the entire cosmos, using telescopes that are straining to see the very edge of reality. Their fleeting existence and immense distance place them just beyond our current observational grasp, making the hunt for the first starlight one of the most compelling chases in all of modern astronomy. Now, if the first stars are the main characters in our cosmic story, our second great mystery asks the question: what was the cue for them to step onto the stage? What was the specific trigger that finally caused those vast, silent clouds of pristine gas to suddenly collapse and ignite? The early universe wasn't just sitting there, waiting patiently for stars to appear. In fact, for millions of years, it was perfectly content to remain a dark, featureless expanse. The material was there, but it lacked the crucial instruction to start clumping together. The force of gravity was constantly pulling, but it needed a starting point, a tiny imperfection to amplify. Think of it like trying to boil a perfectly smooth pan of water. Without a single tiny bubble or a minuscule scratch on the surface to get things started, the water can actually become superheated, resisting the transition to a rolling boil. The early cosmos was in a similar state of superheated suspense. It was filled with a hot, dense fog of hydrogen and helium, all held in a delicate balance. The key to breaking this standoff lay in the tiniest of seeds, the microscopic density fluctuations imprinted on the fabric of spacetime by the Big Bang itself. These were the quantum ripples, stretched to cosmic proportions, that would become the blueprints for all future structure. But these ripples were incredibly faint. For gravity to get a real grip and begin pulling matter together, the gas needed a way to shed its immense heat and energy. Hot gas is energetic and resists collapse. Cold, dense gas is much more willing to cooperate and form stars. This is where a rather unassuming molecule enters the story as the prime suspect: molecular hydrogen. In the modern universe, star-forming clouds cool down efficiently using heavier elements like carbon and oxygen. But in the primordial world, those elements didn't exist yet. Hydrogen atoms had to find another way. When 2 hydrogen atoms managed to link up and form a molecule, that molecule could then vibrate and rotate in specific ways, effectively converting the gas's thermal energy into faint infrared radiation that could escape into space. This molecular hydrogen cooling was like a cosmic air conditioning system, allowing the densest patches of gas to cool down, quiet down, and finally succumb to the relentless pull of their own gravity. It's widely considered the leading candidate for the primary trigger of the first star formation. However, many scientists wonder if this humble molecule was truly powerful enough to single-handedly kick-start the entire cosmic dawn. The cooling from molecular hydrogen was surprisingly inefficient compared to the processes we see today. Was it enough to overcome the gas pressure and the counteracting effects of the leftover radiation from the Big Bang? This uncertainty has led to a fascinating debate, with researchers proposing other potential co-conspirators that could have given gravity the extra nudge it needed. One compelling idea involves the mysterious influence of dark matter. We know these first stars didn't form in a vacuum. They were born deep within the first halos of dark matter, invisible scaffolds that gathered the hydrogen gas in the first place. If dark matter particles can interact with each other, not just through gravity but by colliding and annihilating, they could have injected a significant amount of extra heat into the collapsing gas. This sounds counterintuitive. Wouldn't more heat prevent collapse? Actually, under the right conditions, this added energy could have stirred the gas, preventing it from fragmenting into many small stars, and instead encouraging the formation of the single, massive behemoths our models predict. Another proposed trigger involves the first bursts of cosmic rays, or even the radiation from the earliest black holes. These high-energy particles could have ripped electrons away from hydrogen atoms, creating ions that were much more effective at radiating away heat. It's a cosmic puzzle where we have several pieces that seem to fit, but we're not entirely sure of the final picture. The transition from a smooth, dark universe to one illuminated by starlight hinged on this delicate and complex chain of events. Unraveling the exact sequence isn't just an academic exercise. It's about identifying the precise moment that the universe shifted from a simple state of being to a complex state of becoming, setting in motion the chain of events that would eventually lead to us. Just as the very first stars were unlike anything in our current night sky, their life stories were epic dramas of intense power and swift conclusions. To grasp their scale, try to picture a star so luminous that its light output rivaled that of a million suns like our own. A single one of these primordial giants could outshine an entire globular cluster, one of those dense balls of hundreds of thousands of stars that orbit our Milky Way. Their brilliance wasn't just a matter of raw power. It was born from a unique and violent efficiency. Since they were composed only of hydrogen and helium, their cores had to reach staggering temperatures and pressures to kickstart nuclear fusion. This resulted in surfaces that were phenomenally hot, possibly glowing with a searing ultraviolet light that we would perceive as an almost pure, harsh blue-white. Their sheer mass forced them to burn their nuclear fuel at a breakneck, extravagant pace. While our stable sun is in the comfortable middle age of its 10 billion-year life, a massive population, 3-star, might have lived its entire turbulent existence in just 2 or 3 million years, a fleeting moment on the cosmic timescale. This incredible luminosity had a transformative effect on the cosmos itself. As these beacons ignited, their powerful ultraviolet radiation began to flood the surrounding space. They acted like cosmic blowtorches, slamming into the neutral hydrogen gas that filled the universe and blasting electrons away from their atomic nuclei. This process, known as cosmic reionization, fundamentally changed the nature of intergalactic space, turning it from a dense, opaque fog into the transparent, ionized medium we observe between galaxies today. Each of these stars could ionize a vast bubble of space around it, creating the first clear regions in the universe and paving the way for light to travel freely for billions of years. Their deaths were as influential as their lives, and the manner of their demise depended entirely on their final mass. For stars between about 80 and 250 times the mass of our Sun, the final act was one of ultimate self-destruction, the pair instability supernova. In the star's collapsing core, temperatures become so astronomically high that the energy itself spontaneously converts into pairs of electrons and positrons. This process catastrophically removes the radiation pressure supporting the star's core, leading to a total and runaway thermonuclear explosion. The star wouldn't just collapse, it would be completely and utterly obliterated, disintegrating in a blast so powerful that it would temporarily shine brighter than all the other stars in its nascent galaxy combined. This type of explosion would leave no remnant behind, no black hole, no neutron star, just an expanding cloud of newly forged elements. For the very most massive stars, those tipping the scales at over 250 solar masses, the end was even more direct and strangely silent. Their gravity was so overwhelmingly powerful that after they exhausted their nuclear fuel, the core's collapse would be unstoppable. No supernova shockwave could overcome that immense gravitational pull. Instead, the entire star would simply implode, collapsing directly into a black hole without a visible explosion. You can imagine the profound silence of such an event, a titan of the early cosmos simply winking out of existence, leaving behind only a gravitational pit in spacetime. Yet even this seemingly sterile end played a crucial role, as these direct collapse black holes are the leading candidates for the seeds of the supermassive black holes we find at the centers of galaxies today. Regardless of how they died, the supernovae of the first stars were the universe's first great chemical laboratories. They were the crucibles where the first significant amounts of elements heavier than helium were forged: carbon, oxygen, neon, and iron. In their violent deaths, they scattered these newly minted atoms far and wide, polluting the pristine hydrogen and helium gas of the cosmos. This metallic enrichment, as astronomers call it, was a point of no return. It forever altered the chemical composition of the universe, ensuring that the next generation of stars would form from gas that was already slightly seeded with these heavy elements. This single change made the formation of smaller, longer-lived stars like our Sun possible, and ultimately set the stage for the creation of rocky planets and the chemistry of life itself. But with such spectacular deaths, you'd think we'd have found their remains by now, right? This brings us to our fourth great mystery: the frustrating, exhilarating, and utterly cutting-edge search for direct evidence of population 3 stars. For all our sophisticated theories and breathtaking simulations, the existence of these first giants remains a brilliant, compelling ghost story until we can point to a telescope and say, "There." That's one. The hunt for them is a cosmic detective story playing out in real time. A case that hinges on finding the faintest of clues across unimaginable gulfs of space and time. Astronomers are pursuing 2 main lines of investigation, one looking out to the edge of the observable universe, and the other looking deep into our own cosmic backyard. The first method is a direct assault on the problem, using our most powerful observatories, like the James Webb Space Telescope, to peer back to the era of the very first galaxies in the hopes of catching a glimpse of a population 3 star in its final explosive death throes. We're not necessarily looking for the star itself, but for the unique signature of a pair instability supernova. These explosions are predicted to be incredibly bright and to have a very specific light curve, a particular pattern of how they brighten and fade over time, that is distinct from all other types of stellar explosions. The challenge is immense. These events are incredibly rare and fleeting, lasting only a few months. Finding one requires not just a powerful telescope, but also a great deal of luck, continuously monitoring vast patches of the sky in the faint hope that one of these cosmic fireworks will ignite during an observation campaign. It's a waiting game on a billion-year timescale. The second, and perhaps more promising, approach is a form of cosmic archaeology. Instead of looking for the stars themselves, we search for their chemical fossils. When a population 3 star died in a pair instability supernova, it scattered its uniquely pure cargo of newly forged elements into the surrounding gas. The next generation of stars that formed from that polluted material would then carry that specific chemical fingerprint in their atmospheres. So, astronomers are scouring our own Milky Way galaxy for its most ancient inhabitants, stars that are incredibly metal-poor. The star known as SMSSJ03 1300 36,670,839 3 is a perfect example. It's one of the oldest stars ever discovered, and its atmosphere is almost completely devoid of iron. The amount of iron it has is so minuscule it's equivalent to a single drop of water mixed into an Olympic-sized swimming pool. This stark absence tells a clear story. This star must have formed from gas that was enriched by a single previous supernova. And not just any supernova, but one from a massive population, 3 star that underwent a pair instability explosion. The chemical pattern in this ancient star's atmosphere is like a preserved crime scene, pointing directly to the specific type of progenitor that seeded the cloud from which it was born. It's not a direct sighting of a first star, but it's the next best thing. A piece of compelling circumstantial evidence that links us directly back to one of the universe's very first stellar explosions. This is where the James Webb Space Telescope enters the story as a game-changer. For the first time, we have an instrument with the sensitivity and the infrared vision capable of potentially seeing the light from the first stars and their host galaxies. Webb is currently staring deep into fields like the Hubble Ultra-Deep Field, gathering light that has been traveling for over 13 billion years. Every new dataset it sends back is scoured for any anomaly, a faint red dot that might be a galaxy powered predominantly by these first-generation stars, or a transient flash of light that matches the predicted signature of a pair instability supernova. The search is painstaking. The signals are achingly faint, and astronomers must carefully distinguish these primordial objects from closer, dimmer stars or more recent galaxies that just happen to look similar. It's a monumental task of sifting through cosmic noise to find that one elusive signal. The very fact that we are now, today, technologically capable of mounting this search is a testament to human curiosity and ingenuity. We are literally building machines to look back to the beginning of time, to witness the moment the darkness ended, and every new observation brings us one step closer to finally laying eyes on the ghosts that illuminated the cosmos. Just as the first stars were rewriting the rules of stellar life, their deaths were simultaneously creating a new, even more extreme class of cosmic object, the very first black holes. This is our fifth great mystery, and it's a fundamental one. How did black holes, these gravitational abysses from which not even light can escape, first appear in a universe that was only filled with smooth, simple gas? The answer is not straightforward, and astronomers are currently split between 2 dramatically different origin stories, each with profound consequences for everything that followed. The first and more traditional theory paints a direct line from the death of the massive population, 3 stars we just discussed. In this scenario, the first black holes are stellar corpses. When a truly massive star, perhaps 60 times heavier than our Sun or more, reaches the end of its brief, fiery life, its core collapses under its own immense weight. If the resulting supernova explosion is not powerful enough to blow all the material away, the remaining core continues to collapse, crushed into a singularity, a point of infinite density, and a black hole is born. These first-generation stellar black holes would have been relatively small, perhaps just a few dozen times the mass of our Sun. They would have been scattered across the early cosmos, the dark remnants of the first stellar titans. From these modest beginnings, they could then begin to grow by voraciously feeding on the surrounding gas, or by merging with one another over billions of years. It's a logical, step-by-step process, building cosmic giants from tiny seeds. But there's a major problem with this neat and tidy story, and it's a problem of time. At the centers of many galaxies, including our own Milky Way, we find supermassive black holes, monsters weighing millions or even billions of times the mass of our Sun. The real head-scratcher is that we can see fully grown supermassive black holes in the form of incredibly bright quasars, when the universe was less than 1 billion years old. For a black hole seed born from a single star to grow that big, that fast, it would have to feed at a breakneck pace, almost non-stop, right up against the theoretical limits of physics. It's like expecting a newborn sapling to grow into a 1,000-year-old redwood tree in just a few decades. The math is incredibly challenging, which has led scientists to propose a far more radical and violent alternative. This second theory suggests that the first black holes didn't need a star to die at all. Instead, they were born directly from the collapse of primordial gas clouds, skipping the stellar stage entirely. Imagine one of those vast, pristine clouds of hydrogen and helium we talked about earlier. Under the right conditions, if the cloud couldn't cool down efficiently enough to fragment into many smaller stars, it could simply collapse in on itself as a single, monstrous entity. This isn't a star forming, it's a whole gas cloud undergoing a gravitational breakdown. Without nuclear fusion at its core to provide outward pressure and hold it up, the entire structure, amounting to tens of thousands, or even hundreds of thousands, of solar masses of gas, would plummet directly into a gravitational vortex, forming a black hole in one single, colossal step. It's the difference between building a campfire log by log and suddenly having an entire forest spontaneously combust into a single, vast inferno. These direct collapse black holes would be born as supermassive from day one, or at least as heavyweight seeds, thousands of times more massive than their stellar-born cousins. This gives them a huge head start in the cosmic growth race, easily solving the timing problem of the early quasars. But for this spectacular event to occur, the conditions had to be just right. The gas cloud needed to be massive, and crucially, it had to avoid cooling down and splitting apart. This is where the intense ultraviolet light from a nearby, massive population, 3-star might have played a surprising role. This radiation could have flooded the cloud, breaking apart the fragile molecular hydrogen that acted as the primary coolant. By effectively sterilizing the cloud and preventing it from forming normal stars, the radiation could have doomed it to its direct, catastrophic collapse into a black hole. It's a fascinating and ironic possibility. The first starlight might have been the very trigger that created the first black holes, not from its death, but from its brilliant, life-giving energy. The implications of this mystery stretch all the way to the present day. The path by which the first black holes formed determined the initial conditions for the growth of every supermassive black hole we observe. Did they start small and grow fast against all odds, or were they simply born giants? The answer lies encoded in the properties of the most distant quasars and the faint, ancient black holes lurking in nearby galaxies. By studying their masses and their feeding habits at different cosmic epochs, astronomers are working backwards, piecing together their origin story. This isn't just about understanding exotic objects in deep space. It's about tracing the lineage of the gravitational hearts that anchor galaxies, that control star formation, and that ultimately shape the large-scale structure of the universe we inhabit. The birth of the first black holes was a pivotal fork in the cosmic road, and we are still trying to determine which path the universe actually took. But this transformation didn't happen instantly. The cosmic dark ages didn't end with a sudden flash. It was more like a slow, patchy dawn. For hundreds of millions of years, the first stars and galaxies flickered to life, each one creating a growing, glowing bubble of ionized space around itself. Think of it like a dense, global fog slowly being burned away by countless campfires igniting one by one. These individual bubbles of transparency grew and expanded, eventually overlapping and merging, until the entire cosmic fog had lifted. The process of reionization was likely a complex and messy one, not a smooth, uniform event. Dense regions of gas, perhaps near massive clusters of early galaxies, would have become transparent first, while more isolated, lonelier voids in the cosmic web might have held onto their neutral hydrogen for much longer. The timeline for this grand transition is a key piece of the puzzle. Based on observations of the most distant quasars and the cosmic microwave background, we know that reionization was largely complete by the time the universe was around 1 billion years old. But when did it start? How long did it truly take? Was it a swift process, driven by an explosive surge of early starlight, or a more gradual and drawn-out affair? The answers to these questions are crucial because they tell us about the overall efficiency and the collective power of the very first generations of luminous objects. This leads us directly to the central and still unresolved mystery. What exactly were the primary architects of reionization? Was it the work of a few incredibly brilliant and massive stars, or the combined effort of a vast population of smaller, more common ones? Let's consider the case for the Titans. Those first, monstrous population, 3 stars were phenomenally efficient at producing ionizing photons. A single one of these behemoths could have output as much ultraviolet radiation as an entire cluster of modern stars. If they were common in the earliest epochs, a relatively small number of them could have done the job, punching large, clean bubbles into the neutral hydrogen very quickly. This scenario would suggest that reionization began early and was driven by powerful, localized sources. However, these giants lived fast and died young. Their fleeting lifetimes mean that their contribution, while intense, might have been brief, like a series of brilliant camera flashes illuminating a dark room for only a moment. On the other hand, perhaps the real workhorses were the first small galaxies. After the first few generations of stars polluted the gas with heavy elements, star formation could proceed in a more normal way, creating vast numbers of smaller, longer-lived stars. While each individual dwarf galaxy was faint, their collective numbers could have been staggering. The combined ultraviolet output from billions upon billions of these tiny, faint galaxies, shining steadily for hundreds of millions of years, could have provided a more sustained and widespread ionizing background. This would be a slower, more uniform process, like a slowly brightening sky before sunrise. The James Webb Space Telescope is poised to be the ultimate arbiter in this debate. By counting the number and measuring the brightness of these ultra-faint, early galaxies, it can tell us if there were enough of them to provide the total ionizing power needed. Early results are fascinating, suggesting an abundance of small, bright galaxies in the very early universe, potentially tipping the scales in favor of this collective population. Yet, the ghostly presence of those first brilliant giants cannot be entirely ruled out. The truth likely lies in a complex combination. A cosmic relay race where the massive population 3 stars started the process, creating the first clear patches, and then countless smaller galaxies finished the job, flooding the universe with a steady, pervasive light that finally burned away the last vestiges of the primeval fog. This universal transformation, the lifting of the cosmic fog, stands as one of the most significant events in the history of the universe. Yet we still grapple with a fundamental question: who exactly flipped the switch? The prime suspects are lined up, but pinning the blame on one requires us to be cosmic forensic scientists, examining the evidence left behind in the ancient light that reaches us today. The case against the first massive stars is compelling. As we've seen, a single population 3 giant was an ultraviolet production factory, flooding its surroundings with ionizing photons far more efficiently than any star we know today. If these titans were numerous enough, they could have acted as powerful blowtorches, carving out vast, transparent bubbles in the neutral hydrogen gas with remarkable speed. Their sheer intensity makes them a natural suspect for starting the reionization process early and aggressively. But there's another, more shadowy culprit in the lineup: the first active black holes, often called mini-quasars. When those early black holes began to feed, the gas spiraling into them didn't just vanish quietly. It formed a superheated accretion disk, glowing with such ferocious intensity that it could outshine an entire galaxy. This process produces a tremendous amount of high-energy radiation, including the hard ultraviolet and even X-ray photons that are exceptionally good at ionizing hydrogen. A single, voracious mini-quasar could have been an even more potent source of ionizing energy than a cluster of the first stars, potentially reionizing enormous volumes of space from the inside out. The debate, therefore, isn't just about stars versus galaxies. It's about whether the primary engine of reionization was the brilliant thermal glow of stellar surfaces or the violent gravitational power released from the edge of a black hole's abyss. Perhaps the most likely scenario is that it was a messy, collaborative effort, a cosmic relay race where different players took the lead at different times. The first, spectacularly massive stars may have ignited the process, creating the initial network of ionized bubbles, but their short lifetimes meant their contribution was fleeting. As they died, they seeded the universe with heavy elements and also left behind black hole remnants. These black holes then began to grow and feed, their mini-quasar phase providing a second, sustained wave of ionizing radiation. Meanwhile, the first small galaxies, now forming in greater numbers from slightly enriched gas, contributed a steady, pervasive background of ultraviolet light from their countless smaller, longer-lived stars. The challenge for astronomers is that we cannot simply look back with a telescope and watch this happen directly. The era of reionization is shrouded in the very hydrogen fog it sought to erase. The same neutral gas that was being ionized also absorbs the most direct light from the sources responsible, hiding them from our view. So, we have to become detectives of the indirect, using clever proxies to piece together the story. One of the most powerful pieces of evidence comes from the oldest light we can see, the cosmic microwave background. This afterglow of the Big Bang carries a subtle imprint from its journey through the reionizing universe. As the CMB photons traveled through the growing bubbles of ionized gas, they had a small but measurable chance of scattering off the free electrons within them. This scattering leaves a specific, polarized pattern on the CMB, a faint fingerprint that allows us to estimate the total amount of scattering that occurred. By measuring this, satellites like Planck have told us that reionization was roughly halfway complete by the time the universe was about 550 million years old. This gives us a crucial anchor point for the overall timeline, but it doesn't tell us what caused the scattering, whether it was starlight or quasar radiation. For that, we turn to another brilliant forensic tool, the Lyman-alpha forest. When we look at the spectrum of a distant quasar, we don't see a clean, continuous band of color. Instead, we see a forest of dark absorption lines superimposed on it. These lines are created by clouds of neutral hydrogen gas at different distances along our line of sight, each cloud absorbing a very specific wavelength of the quasar's light. The distribution of these lines is a direct record of the state of the intergalactic medium throughout cosmic time. As reionization proceeds, the number of these neutral hydrogen clouds decreases, and the gaps in the forest, the regions where the light comes through unimpeded, grow larger. By studying the Lyman-alpha forest in the spectra of the most distant quasars, we can map the progress of reionization. We can see when the universe was mostly neutral, when it was a patchwork of ionized and neutral regions, and when it became fully transparent. Furthermore, the specific properties of the absorption can offer clues about the hardness of the ionizing radiation, potentially helping to distinguish between the softer UV from stars and the harder, more energetic photons likely produced by accretion disks around black holes. It is through this painstaking, indirect detective work, combining the snapshot from the CMB with the detailed timeline from the Lyman-alpha forest, that we are slowly closing in on the identity of the sources that ended the Dark Ages and lit up the cosmos for good. As our cosmic story unfolds, we arrive at a pivotal moment of construction, a time when the first isolated stars began to gather into communities, forming the earliest building blocks of the grand structures we see today. This is the mysterious era of the first protogalaxies. These were not the magnificent spirals or elegant ellipticals we now photograph. They were tiny, fragile things, perhaps only 1/10,000th the mass of our own Milky Way, containing maybe 1 million stars huddled together within a vast, invisible shroud of dark matter. The formation of these first galactic seeds is one of the most active and complex areas of research in cosmology, because it represents the critical transition from a universe of individual actors to one of organized society. How exactly did these initial clumps emerge, and what were the rules that governed their chaotic and violent mergers? The answers are encoded in the very architecture of every galaxy we see, including our own. The prevailing theory that guides our understanding is known as the hierarchical, or bottom-up, model of structure formation. Imagine the early universe not as a place where giant galaxies simply popped into existence, but as a cosmic construction site where the smallest bricks were laid first. The fundamental blueprint for this entire process was drawn by the dark matter. In the millions of years after the Big Bang, slight density fluctuations in the dark matter began to amplify, pulling in more and more dark matter through gravity. These grew into the first halos, roughly spherical, invisible scaffolds that began to dot the cosmos. Ordinary matter, the hydrogen and helium gas, was then drawn into these gravitational wells. As the gas fell in, it condensed, cooled, and eventually fragmented to form the very first stars. So, a single protogalaxy was essentially a dark matter halo that had managed to light up with its first generation of stellar inhabitants. This bottom-up picture suggests our mighty Milky Way was not born in a single, glorious event, but was painstakingly assembled over billions of years from the cannibalized remains of thousands of these smaller protogalactic precursors. But the physics of how these tiny structures actually merged is where the mystery truly deepens. When two protogalaxies, each embedded in its own dark matter halo, drifted close enough together, their mutual gravitational attraction would begin to pull them into a cosmic dance. However, this was not a gentle waltz. It was a violent and chaotic tango. As the halos intertwined, their dark matter components, which rarely interact with anything except through gravity, would mostly pass right through each other. The stars, being so small and far apart, had a very low chance of physically colliding. It was the gas that experienced the full brunt of the violence. The gaseous components of the two protogalaxies would slam into each other at tremendous speeds. These colossal collisions created immense shock waves that rippled through the gas, compressing it violently and triggering ferocious waves of new star formation, known as starbursts. A relatively quiet pair of protogalaxies could, upon merging, suddenly ignite into a brilliant firestorm of stellar birth, shining far more brightly than the sum of their parts. These early mergers were far more than just a mechanism for making bigger galaxies. They were fundamental in setting the evolutionary path for all future galactic development. The specific way a protogalaxy merged, its angle, its speed, the ratio of its mass to its partners, could determine the ultimate fate of the resulting object. Think of it as a cosmic roll of the dice. A series of gentle, head-on mergers between roughly equal-sized protogalaxies would tend to randomize the orbits of stars, creating a more blob-like spherical structure without a disk. This is the path astronomers believe leads to the formation of elliptical galaxies. On the other hand, if a larger protogalaxy steadily absorbed a stream of much smaller satellites, the orderly rotation of the central structure could be preserved. The incoming gas would sink to the center, settling into a spinning disk and giving rise to a spiral galaxy like our own. The incredible diversity of galaxy shapes we observe today, the stately spirals, the fuzzy ellipticals, the irregular oddballs, can all be traced back to the unique merger histories of their protogalactic ancestors. The central enigma that remains is pinpointing the exact properties of those very first dark matter halos and the protogalaxies they hosted. How small could they actually get? Simulations suggest the very first stars might have formed in halos as light as just 1 million times the mass of our Sun, truly minuscule by galactic standards. Detecting these primordial building blocks is one of the ultimate goals of telescopes like the James Webb Space Telescope. It searches for ultra-faint, reddish smudges of light that could be these infant systems. Furthermore, the nature of dark matter itself is written into this process. The coldness of dark matter, meaning its particles move relatively slowly, is a key ingredient in the bottom-up model. If dark matter were warm and faster moving, it would suppress the formation of very small halos, changing the entire initial conditions of galaxy assembly. By studying the faintest and most ancient galaxies, we are indirectly testing the fundamental properties of the dark matter that orchestrated their birth. The assembly of the first protogalaxies was the universe's first great experiment in urban planning, and the sprawling galactic metropolises we see today are the living results of those ancient, foundational construction projects. Yet for all its apparent emptiness, space is far from vacant. A mysterious, invisible substance, dark matter, permeates every corner of the cosmos, an unseen architect that provided the essential scaffolding upon which the first stars and galaxies were built. We cannot see it, touch it, or directly measure it with any instrument we have yet devised. Yet we know it is there because of its profound gravitational influence. In the early universe, it was dark matter that acted as the cosmic foreman, gathering the raw materials and constructing the gravitational wells that allowed ordinary matter to finally clump together and ignite. Without this invisible framework, the universe might have remained a forever dark and featureless expanse, a silent sea of hydrogen and helium with no stars to light the way. The leading theory, which forms the bedrock of modern cosmology, posits that dark matter is cold. This doesn't mean it's chilly in the way we think of temperature, but rather that its hypothetical particles move relatively slowly compared to the speed of light. This coldness is crucial. Slow-moving particles are easily caught by their own gravity, allowing them to rapidly clump together on even the tiniest of scales. According to this cold dark matter model, the very first structures to form in the universe were minuscule halos of dark matter, emerging from the faint quantum ripples of the Big Bang. These microscopic seeds then hierarchically merged, building up larger and larger structures in a bottom-up fashion, from the size of a small asteroid all the way up to massive galaxy clusters. It's a beautifully simple and powerful idea that has successfully predicted the large-scale distribution of galaxies we observe across the sky. The first stars, according to this view, ignited deep within these smallest, densest clumps of dark matter, their formation directed and enabled by this unseen gravitational hand. However, a fascinating mystery persists, one that challenges this very foundation. What if dark matter isn't perfectly cold, but instead warm? Warm dark matter would consist of particles that are much lighter and faster moving. This simple change in property would have dramatic consequences for the early universe. Those fast-moving particles would have enough energy to stream away from the tiniest gravitational potentials, effectively washing out and erasing the smallest density fluctuations. In a warm dark matter cosmos, there would be a fundamental lower limit to the size of the first structures. Instead of a universe built from the bottom up with countless tiny dark matter clumps, the first halos to form would be much larger, perhaps the size of small dwarf galaxies from the very start. This would create a top-down scenario where larger structures fragment into smaller ones, a complete reversal of the traditional picture. The observable signature of this would be a striking absence, a lack of the very smallest, faintest dwarf galaxies orbiting around larger galaxies like our Milky Way. The fact that we do observe such ultra-faint dwarfs is a point in favor of the cold model, but the debate is far from settled, as other processes could also suppress the formation of these tiny galaxies. The properties of dark matter don't just affect the scale of the first structures. They also influence the internal anatomy of those first protogalaxies. In the cold dark matter scenario, the dark matter halo develops a steeply rising density profile towards its center, what scientists call a cusp. This dense, central cusp of dark matter provides a deep, strong gravitational well that can efficiently pull in gas and trigger vigorous star formation right from the outset. But some observations of nearby dwarf galaxies show evidence of a constant density core at their centers instead of a cusp, which is harder to explain with the simplest cold dark matter models. This has led to proposals for even more exotic possibilities, like self-interacting dark matter, where the invisible particles can actually collide and scatter off one another. These collisions would transfer energy from the dense center out to the edges, effectively erasing the cusp and creating a soft core, much like stirring a cup of coffee evens out the concentration of sugar. The way the first stars and galaxies assembled themselves, their brightness, their distribution, and even their survival, are all direct reflections of the hidden nature of the dark matter that birthed them. Ultimately, the quest to understand the first luminous objects is inextricably linked to the quest to understand the dark universe. We are using the ancient light from the first galaxies as a cosmic laboratory to probe the fundamental physics of something we cannot see. The timing of the cosmic dawn, the brightness of the most distant galaxies now being found by the James Webb Space Telescope, and the precise arrangement of galaxies across the sky all serve as data points in a grand experiment. Each new observation helps to constrain the possible properties of dark matter, telling us what it can and cannot be. The invisible architect left its signature in the blueprints of creation, and by carefully studying the first structures that emerged, we are learning to read that signature, slowly bringing the mysterious substance that shapes our cosmos out of the shadows. This journey from a universe of pure simplicity to one of complex chemistry hinges on a monumental transformation, the birth of the very first heavy elements. In the language of astronomy, every element heavier than helium is called a metal. It's a quirky bit of jargon, but it highlights a fundamental divide. To an astronomer, the oxygen you breathe, the calcium in your bones, and the iron in your blood are all considered metals. For nearly 100 million years after the Big Bang, the cosmos was utterly metal-free, a pristine expanse of only hydrogen, helium, and a whisper of lithium. There was no material for rocks, no oxygen for water, no carbon for the molecules of life. The universe was a vast chemical desert, waiting for its first rain. The transformation began when the first massive stars ignited. Inside their incredibly hot and dense cores, these stellar furnaces initiated a process called nuclear fusion, forcefully smashing the nuclei of hydrogen and helium atoms together. This is where the alchemy of the cosmos truly began. Through a series of step-by-step reactions, the intense heat and pressure fused hydrogen into helium, then helium into carbon, and carbon into ever heavier elements like oxygen, neon, and magnesium. For the first time in cosmic history, new atomic nuclei were being manufactured. But this process had a natural limit. The first stars could only forge elements up to a certain point on the periodic table, roughly as heavy as iron. Creating anything heavier required an even more violent and explosive event. This is where the spectacular deaths of these stars entered the stage. When a massive population, 3-star, reached the end of its brief life and exploded as a supernova, the cataclysm became the universe's ultimate pressure cooker. The shockwaves roaring out from the collapsing core created a frantic, chaotic environment where atomic nuclei were bombarded with a tremendous flood of neutrons. In a rapid series of captures known as the R process, or rapid neutron capture process, existing seed nuclei could greedily absorb these neutrons, bloating into heavier and heavier isotopes. These unstable isotopes would then undergo radioactive decay, settling into stable forms of elements like gold, silver, platinum, and uranium. In a single brilliant flash, A star could synthesize the entire range of elements and scatter them across light years of space, seeding the surrounding gas clouds with the raw ingredients for future planets and, one day, living organisms. The central puzzle that captivates scientists is tracing the precise pathway of this chemical enrichment. How did we get from a universe with zero metals to one where a small, rocky world like Earth could form, rich with the diversity of elements necessary for life? The process was undoubtedly gradual and patchy. The earliest supernova created isolated, expanding bubbles of slightly enriched material. These were the first polluted regions in the cosmos. The next generation of stars that formed inside these bubbles therefore began their lives with a tiny but crucial metallic heritage. These second-generation stars were fundamentally different from their predecessors. Even a minuscule amount of heavy elements made the gas clouds from which they formed much more efficient at cooling and fragmenting. This allowed for the formation of smaller, longer-lived stars, much more like our own Sun. Over hundreds of millions of years, this cycle of star formation, metal production, and dispersal through supernova repeated over and over. Galaxies began to act like giant recycling plants. Stars would form from enriched gas, live their lives, and then explode, ejecting even more processed material back into the galactic reservoir. This continuously cycling gas became chemically richer with each passing generation. The interstellar medium within galaxies transformed from a pristine primordial gas to a complex chemical soup. The challenge for astronomers is that we cannot rewind this film. We have to piece it together by looking at the chemical compositions of the oldest stars we can find, using them as fossil records of the early galactic environment. By studying the atmospheres of ancient, metal-poor stars within our own Milky Way, we can read this cosmic history book. A star like SMSS J0313, with its almost complete lack of iron, tells us it formed from gas polluted by just one or two previous supernovae. Other ancient stars show different chemical patterns, some rich in carbon, others in elements like strontium. Each pattern a clue pointing to the specific mass and explosion type of the progenitor star that came before it. It's a monumental task of forensic astronomy, connecting the chemical fingerprints in the oldest stellar fossils back to the specific kinds of stellar lives and deaths that created them. This intricate detective work is slowly revealing the step-by-step chemical evolution that turned a barren, primitive universe into a cosmos capable of forging a planet that could one day ask questions about its own origins. As we trace the journey of these first heavy elements, we encounter our 11th great mystery, one that moves beyond their creation to their cosmic dispersal. How did the iron forged in that first supernova, or the carbon synthesized in a stellar core, actually travel from its birthplace to seed new worlds? The early universe didn't have a giant spoon to stir its contents. The distribution of these inaugural metals was a chaotic and haphazard process, creating a dramatic and uneven patchwork across the cosmos. Instead of a uniform enrichment, the first several hundred million years likely resembled a landscape of isolated chemical islands emerging in a vast, pristine sea. Each brilliant, short-lived giant star acted as a solitary chemical factory. When it died in a cataclysmic supernova, the explosion would blast its newly forged elements outward in a rapidly expanding shell of hot, metal-rich debris. This created a growing bubble of polluted gas, a single region of slightly enriched material adrift in an ocean of pure hydrogen and helium. For a long time, vast tracts of the universe remained in their original, primordial state, completely untouched by this stellar fallout. The size and reach of these polluted bubbles were determined by the sheer power of the supernova explosion itself. A titanic pair instability event, which completely unbinds the star, could catapult its elemental cargo across thousands of light years, creating an enormous chemical oasis. A less energetic collapse, perhaps one that left behind a black hole, might only distribute its metals a much shorter distance, resulting in a smaller, more concentrated chemical hotspot. This meant the initial metallicity of the universe wasn't a smooth gradient. It was a wildly fluctuating map of have and have-not regions, a cloud of gas fortunate enough to be caught in the blast wave of several early supernovae could become relatively enriched quite quickly. Another cloud, just a few thousand light-years away in a cosmic void, could remain in a perfectly pristine condition for millions of years longer, a perfect relic of the primordial cosmos. The fate of a gas cloud, whether it would form a new star that was metal-poor or metal-rich, depended entirely on its location relative to these first, scattered stellar graveyards. This is where the ancient stars within our own Milky Way galaxy become our most vital time capsules. Scattered throughout the halo of our galaxy are stars so incredibly old and metal-poor that they are effectively living fossils, preserving the chemical conditions of the gas clouds from which they formed over 13 billion years ago. They are the unaltered archaeological records of that early, patchy universe. The star known as 2-Massa J0313, which we mentioned earlier, is a prime example. Its atmosphere contains barely a trace of iron, less than 1/10,000,000th of the iron found in our Sun. This profound absence tells a very specific story. This star did not form from a well-mixed reservoir of gas that had been polluted by many previous generations of stars. Instead, it must have been born from a cloud that was enriched by the debris of just one, or at most two, prior supernova. Its chemical fingerprint is the direct signature of a single pollution event, a snapshot of the isolated chemical bubbles that once dotted the cosmos. Other ancient stars tell slightly different, but equally revealing, tales. Some show a surprising abundance of carbon relative to iron, while others might be rich in elements like strontium but poor in everything else. These peculiar chemical patterns are like distinct dialects of the same primordial language, each one pointing back to the specific type of star that preceded it. A carbon-enhanced star suggests its progenitor was a certain mass and exploded in a particular way. The incredible diversity of chemical signatures among these ancient stellar fossils is direct evidence that the early metal distribution was not uniform. It was a chaotic and stochastic process, where the chemical makeup of a star depended entirely on the luck of the draw, on which supernova remnants happened to drift into its parent cloud. This also implies that pockets of truly pristine gas, completely devoid of any heavy elements, might have persisted for a remarkably long time, perhaps even hundreds of millions of years after the first stars had already lived and died. The hunt for a genuine population, 3-star, one with 0 metals, continues, guided by the understanding that such a relic could only have formed in one of those isolated, untouched regions that escaped the first waves of chemical pollution. Understanding this messy and uneven distribution is absolutely critical for modeling the next great leap in cosmic evolution, the second generation of stars. The transition from the first to the second generation was one of the most important shifts in the history of the universe, and it was governed almost entirely by chemistry. The presence of even a tiny amount of heavy elements dramatically changes how gas behaves. Metals are incredibly efficient at cooling gas clouds. Elements like carbon and oxygen can radiate away thermal energy far more effectively than molecular hydrogen ever could. So, a gas cloud that was enriched with the ashes of earlier supernova could cool down much faster and to a much lower temperature. This efficient cooling allowed the cloud to fragment into much smaller, denser clumps than was possible in the pristine primordial era. Instead of forming a single, monstrous star weighing 100 solar masses, a slightly polluted cloud could break up into a whole cluster of smaller stars, some perhaps as small as our Sun. This is the fundamental reason why the stellar population of the universe diversified so rapidly. The initial patchy distribution of metals directly dictated the mass, the number, and the longevity of the stars in the second generation. It set the stage for the emergence of stable, long-lived stars around which the first rocky planets could eventually coalesce. forever altering the potential for complexity in the cosmos. This transition from the first to the second generation of stars marks one of the most profound and consequential shifts in cosmic history. It was the moment the universe learned how to build for the long term, moving from a series of brilliant, fleeting fireworks to establishing a stable and enduring stellar population. The key agent of this change was the very pollution left behind by the dramatic deaths of the first stars, those first heavy elements, or metals, scattered into the void. These metallic ashes introduced a powerful new physical process into the cosmos: efficient cooling. In the pristine clouds that formed the very first stars, the only coolant available was molecular hydrogen, a relatively weak mechanism for shedding heat. But now, elements like carbon, oxygen, and silicon could radiate thermal energy away with far greater effectiveness. This was like upgrading from a single, small fan to a powerful, industrial-grade air conditioning system. A gas cloud that could cool down more efficiently could also condense into denser, more compact clumps. This dramatic increase in density allowed the cloud to fragment, breaking apart into numerous smaller cores instead of collapsing as one single, monolithic object. The era of the solitary, hundred-solar mass titan was giving way to the age of the stellar cluster, where hundreds or thousands of smaller stars could be born together from the same enriched cloud. This fragmentation process fundamentally altered the distribution of stellar masses. The first generation of stars, population 3, is thought to have had a very top-heavy initial mass function, meaning the vast majority of the stellar material went into creating genuinely massive giants. In stark contrast, the second generation, often called population 2 stars, exhibited a much broader and more balanced mass distribution. For the first time, the universe began to produce vast numbers of stars with masses similar to, or even smaller than, our own Sun. The significance of this cannot be overstated. A star like our Sun has a stable lifespan of around 10 billion years, a timescale long enough for complex chemical processes to unfold on orbiting planets. Those first behemoths, burning through their fuel in just a few million years, offered no such window of opportunity. The emergence of these smaller, stable, long-lived stars was arguably the single most important prerequisite for the eventual rise of biological complexity. It provided the stable energy source around which the first planetary systems could coalesce, and over billions of years, potentially brew the chemistry of life. But the transition was likely not a single, uniform event that swept evenly across the cosmos. Given the chaotic and patchy distribution of the first metals, the shift from population 3 to population 2 stars would have occurred at different times and at different rates in different locations. In regions that were heavily enriched by multiple early supernovae, the second generation could have appeared very quickly, perhaps within just a few million years of the first star's deaths. In more isolated regions, or in pockets of gas that had managed to remain pristine, it's entirely possible that a few last, lonely population 3 giants continued to form for hundreds of millions of years longer. This paints a picture of a young universe that was a complex mosaic of different stellar populations, a cosmic experiment running in parallel under vastly different chemical conditions. The ultimate demise of the population 3 era was not decreed by a central clock, but by the gradual and relentless pollution of the cosmic gas supply, until virtually no pocket of pure hydrogen and helium remained untouched. We can still find the ancient relics of this second generation today. The oldest stars in the halo of our Milky Way galaxy are these very population 2 stars. They are incredibly metal-poor, but not entirely metal-free. Their atmospheres contain heavy elements, but at levels thousands or even millions of times lower than what we see in our Sun. Studying these stellar fossils allows astronomers to peer directly back into the conditions of that transitional era. Their chemical patterns are like intricate time capsules, revealing the specific types of supernova that enrich their birth clouds. Some show an overabundance of carbon, suggesting they formed from gas polluted by a specific type of massive star. Others show a distinct pattern of elements that points to an enrichment source that was not a single star, but perhaps the combined fallout from an entire cluster of the first stellar explosions. Each of these ancient stars tells a piece of the story, helping us map out how the chemical enrichment proceeded and how the star formation process adapted to this new, metallified environment. This critical shift also had a direct impact on the potential for planet formation. Those first, metal-free stars were unlikely to have formed rocky planets like Earth. There was simply no silicon, iron, or magnesium available to coalesce into dust grains and then into planetesimals. The second generation of stars, however, formed from gas that was now seeded with these crucial elements. For the first time, the protoplanetary disks swirling around these new stars would have contained significant amounts of dust and rocky material. This made the formation of terrestrial planets, asteroids, and comets not just possible, but probable. The universe was no longer just a place of stars and gas. It was now becoming a place of worlds. The transition to the second generation of stars was therefore far more than a simple change in stellar demographics. It was the pivotal moment that unlocked the universe's potential for building complex structures, from stable stellar systems to the rocky planets that orbit them, setting the stage for the entire future of cosmic evolution and ultimately for us to be here, tracing this incredible story back to its origins. Pushing our view to the very edge of the observable cosmos, we arrive at a mystery that is both a technical triumph and a profound cosmic puzzle: the identity of the most distant known galaxy. This isn't just about setting a new record in a cosmic record book. It's a direct assault on our fundamental timeline of how quickly the universe could get its act together after the Big Bang. The current champion, a faint red smudge designated JWST 13-0, was spotted by the James Webb Space Telescope and appears to us as it was, a mere 400 million years after the universe began. To put that into perspective, this galaxy is so ancient that we are seeing it at a time when our own solar system was still over 9 billion years in the future. Its light has been traveling for over 13.5 billion years to reach Webb's golden mirrors, a fossil photon from the cosmic dawn itself. Confirming the distance of such an object is a meticulous, painstaking process that relies on a phenomenon called redshift. As the universe expands, it stretches the very fabric of space, and the light traveling through that stretched space gets pulled to longer, redder wavelengths, much like the sound of a receding ambulance siren drops in pitch. The greater the redshift, denoted by the letter Z, the farther away the galaxy and the further back in time we are looking. For a galaxy like JWST 13-0, with a redshift of about 13.2, its light has been stretched by a factor of more than 14. The ultraviolet light it emitted in the blue part of the spectrum has been shifted all the way into the infrared, which is precisely why the James Webb Space Telescope, with its unparalleled infrared sensitivity, is the only instrument capable of seeing it. Astronomers don't just take a pretty picture and guess. They use an instrument called a spectrograph to break the galaxy's faint light into a rainbow, a spectrum, and they hunt for a specific, recognizable pattern of absorption lines caused by hydrogen gas. When they find that pattern, but see it shifted dramatically toward the red end of the spectrum, they can calculate the redshift with extraordinary precision, confirming that they have truly bagged a record breaker. The profound mystery, however, lies not in the confirmation itself, but in the mere existence of such a galaxy at such an early time. Finding JWST 13-0 is like arriving at a construction site expecting to see only a freshly poured foundation, and instead finding a completed skyscraper. Our best models of cosmic structure formation suggested that it should take hundreds of millions of years longer for gravity to pull together enough material to build a galaxy bright enough for us to see from this distance. Yet, there it is, This forces astronomers to confront several startling possibilities. Perhaps the very first stars and protogalaxies formed with breathtaking speed and efficiency, much faster than our computer simulations have predicted. Maybe the dark matter halos that served as the gravitational anchors for these first galaxies were even more effective at pulling in gas than we thought. Or it could be that star formation in these infant systems was radically different, producing an unexpectedly large number of brilliant, massive stars that made the galaxy disproportionately luminous for its size. Each of these explanations would require a significant tweak, or even a major overhaul, to our standard models of the early universe. What we can learn from this faint red smudge is absolutely revolutionary. Its brightness and size offer clues about its mass and how many stars it had already managed to form in that short 400 million year window. Early analysis suggests it contains perhaps 100 million stars, which sounds like a lot, but is actually hundreds of times fewer than the number in our Milky Way. Yet, it appears to be forming stars at a ferocious rate for its size, and it's also surprisingly small and compact, a far cry from the grand spirals we see today. This paints a picture of the earliest galactic building blocks as being incredibly dense and intensely active stellar nurseries. The presence of oxygen, potentially detected in its spectrum, is another bombshell. It means that this galaxy was already polluted with heavy elements forged in an even earlier generation of stars. This tells us that the cycle of star birth, life, and explosive death had already been turning for some time before this light began its journey to us. We are not seeing the absolute first galaxy. We are looking at a product of an already ongoing cosmic process, which pushes the true beginnings of galaxy formation even further back into the unexplored darkness of the very early universe. The race to find an even more distant galaxy is already on, with every new candidate pushing the frontier and testing our understanding of just how rapidly the infant cosmos transformed from a simple, dark expanse into a universe illuminated by structured, complex, and evolving islands of stars. This discovery sent a shockwave through the world of astronomy, forcing a profound and exciting re-examination of our most fundamental theories. When we look at these incredibly ancient galaxies with the James Webb Space Telescope, we aren't just seeing faint, infant structures. We're seeing galaxies that, by all previous accounts, should not be there. They are far too massive, far too bright, and far too evolved for their cosmic age. It's the equivalent of digging in an archaeological site dated to the Stone Age and finding the steel foundations of a modern skyscraper. The standard model of cosmology, the very successful lambda cold dark matter model, provides a detailed timeline for the bottom-up growth of cosmic structure. It predicted that building galaxies of such splendor would take billions of years of gradual mergers and steady star formation. Yet, Webb is showing us that the universe achieved this level of maturity in what amounts to a cosmic blink of an eye. This discrepancy isn't a minor detail. It's a direct challenge to our understanding of how quickly gravity can gather material and how efficiently gas can be converted into stars in the primordial universe. So, how could these cosmic overachievers have formed so rapidly? Astronomers are exploring several compelling, and sometimes radical, solutions. One leading idea focuses on a dramatic increase in star formation efficiency. In the modern universe, the process of turning gas into stars is surprisingly inefficient. Only a small percentage of the available gas in a giant molecular cloud actually ends up inside stars. The rest is blown away by stellar winds or dispersed by feedback from previous supernova. But in the early universe, conditions might have been far more favorable for maximal star production. The gas was much warmer and denser, and without an abundance of heavy elements, it may not have been able to cool and fragment into as many small, failed stars. This could have led to a top-heavy initial mass function, where a much larger fraction of the available gas went into creating high-mass, brilliantly luminous stars. A galaxy forming 100 massive stars instead of 1,000 small ones would appear dramatically brighter, even if its total stellar mass was the same. Essentially, the early universe might have been operating its stellar factories in an all-in mode, producing a brilliant but short-lived population of stars that made these galaxies shine with an unexpected intensity. Another fascinating possibility involves the nature of the stars themselves. What if the first stars weren't just massive, but belonged to an entirely exotic class we no longer see today? We've already discussed the theoretical population 3 stars, but some models suggest they could have formed in incredibly dense, nuclear-powered clusters where stellar collisions were frequent. In such a chaotic environment, stars could have merged, growing to truly monstrous proportions thousands of times the mass of our Sun. These hypothetical supermassive stars would have been astoundingly luminous, burning through their fuel in a few million years before collapsing directly into massive black holes. A single galaxy hosting just a handful of these incredible behemoths could easily account for the surprising brightness Webb is detecting. Their light would dominate the galaxy's output, making it appear as bright as a much larger, more mature system. Their brief, spectacular lives would also explain why we don't see them in the contemporary universe. They were a unique product of those specific, chaotic early conditions, leaving behind only their brilliant ghost in the data and the black hole seeds that would grow to dominate galactic centers. Beyond tweaking the physics of star formation, some scientists are asking if we need to reconsider the very bedrock of structure formation: dark matter. Our standard model relies on cold dark matter, which clumps efficiently from the smallest scales upward. But what if dark matter is slightly warm, with particles that are lighter and faster moving? While warm dark matter generally suppresses the formation of very small structures, it can actually allow the first larger halos to collapse and form stars much more quickly than in the cold dark matter scenario. In this alternative picture, the first galaxies to light up could have been these pre-assembled, larger halos, giving them a significant head start in accumulating gas and forming stars. This would naturally lead to a population of surprisingly bright and massive galaxies very early on. It's a more fundamental revision to our cosmology, but the sheer brilliance of these early galaxies is forcing astronomers to put every single assumption, even the well-tested ones, back on the table for scrutiny. The James Webb Space Telescope, by pushing our view to the very edge of time, hasn't just given us answers. It has handed us a beautiful, complex puzzle, proving that the cosmic dawn holds surprises that will shape our understanding of the universe for decades to come. Just when we think we've grasped the scale of the early universe, we encounter a paradox so immense it seems to defy the very laws of physics: the precocious existence of supermassive black holes. We find them at the hearts of the earliest galaxies, already fully grown and shining as brilliant quasars when the cosmos was barely a toddler, less than 1 billion years old. The current record holder, a quasar harboring a black hole with a mass over 1.5 billion times that of our Sun, was blazing away just 690 million years after the Big Bang. To appreciate just how baffling this is, imagine planting a tiny acorn and returning a few weeks later to find a colossal redwood tree, thousands of years old, already towering over the forest. The time simply does not add up, and this creates what astronomers call the seed problem, one of the most persistent and fascinating headaches in modern cosmology. If these behemoths started out as the stellar mass black holes left behind by the first massive stars, tiny seeds of maybe a few dozen solar masses, then they would need to grow at an astonishing, almost gluttonous rate to reach billions of solar masses so quickly. There is a theoretical speed limit for how fast a black hole can feed, known as the Eddington limit. This is the point at which the intense radiation pressure from the infalling material actually pushes back against the flow of gas, preventing further accretion. To reach the masses we observe in the early quasars, A stellar mass seed would have to consistently consume material at or above this Eddington limit for its entire existence. A feat akin to winning the cosmic lottery over and over again without a single break. While short periods of super-Eddington accretion might be possible, sustaining this for hundreds of millions of years is incredibly difficult to achieve in models. It's like trying to fill a swimming pool with a fire hose that keeps trying to twist out of your hands. The process is inherently self-regulating and unstable. This severe timing crisis has led scientists to propose a far more radical and dramatic origin story, one that bypasses the star stage entirely. This is the theory of direct collapse, a truly apocalyptic birth for a black hole. Instead of forming from a single dying star, imagine an entire primordial gas cloud, a vast reservoir of pristine hydrogen and helium weighing tens of thousands of solar masses. Under very specific conditions, this cloud could avoid fragmenting into countless smaller stars. Perhaps it was bathed in the intense, sterilizing ultraviolet light from a nearby giant star, which broke apart the molecular hydrogen that would have allowed the cloud to cool and splinter. Without this cooling, and without nuclear fusion to halt the inevitable, the entire colossal cloud would undergo a gravitational runaway. It wouldn't form a star. It would simply collapse directly into a black hole in one single cataclysmic event. This would create a heavyweight seed from day one, a black hole born with a mass of 10,000 solar masses or more, giving it a monumental head start in the growth race, and easily solving the timing problem of the early quasars. But the universe rarely offers simple solutions. For every elegant theory, there are complications and competing ideas. The direct collapse model requires a very particular and possibly rare set of circumstances: a massive gas cloud, a strong external source of ultraviolet radiation, and a near-total lack of metals to prevent efficient cooling. Were these conditions common enough in the early universe to produce the thousands of supermassive black holes we infer must exist? Or could there be another, even more exotic pathway? Some researchers suggest that dense, nuclear star clusters could have been the incubators. In these chaotic environments, where stars are packed together like commuters on a rush-hour subway, frequent collisions could have led to the formation of a single, supermassive star that would then swiftly collapse. Others have explored the wild possibility of mergers between these different types of seeds, or the role of dark matter, though these remain highly speculative. The truth is, we may be dealing with a cosmic ecosystem that employed multiple methods. Perhaps some supermassive black holes were born giants through direct collapse, while others grew rapidly from stellar seeds under a perfect storm of ideal feeding conditions. The hunt is now on to find the missing links, the intermediate mass black holes that would represent the adolescent phase of these giants. Finding them would provide the crucial evidence needed to finally piece together the origin story of the most powerful and enigmatic objects in the cosmos, the gravitational hearts that have shaped galaxies since the very beginning. But this cosmic recycling process had a violent, transformative side effect, one that fundamentally shaped the future of star formation. When those first titanic stars reached the end of their lives and exploded, the shockwaves that tore through space didn't just spread new elements. They delivered an immense jolt of energy to the fragile environments around them. This is the powerful and paradoxical phenomenon of cosmic feedback, and understanding its impact in the infant universe is a major puzzle. A single supernova from a massive population, 3-star, could release more energy in a few months than an entire modern galaxy of stars. That energy had to go somewhere, and it violently interacted with the very gas clouds that were the raw material for future stars. The central question is whether these colossal explosions acted as creators or destroyers in their nascent galactic neighborhoods, and the evidence suggests they were likely both, their influence a dramatic and double-edged sword. On one hand, these blasts were incredibly destructive. Imagine a supernova shockwave expanding at millions of miles per hour. slamming into the surrounding reservoir of cold, dense hydrogen gas. The first and most immediate effect was intense heating. The blast wave would raise the temperature of the gas from a chilly few hundred degrees to many millions of degrees, transforming it into a hot, high-pressure plasma. Hot gas is energetic and resists gravitational collapse. It simply cannot condense to form new stars. Even more dramatically, this heated gas could achieve escape velocity from the shallow gravitational well of its small host protogalaxy. The explosion would literally blow the gas clean away, ejecting it back into intergalactic space in a vast, expanding bubble. For a small protogalaxy, which might have only contained enough gas for a few million stars, losing a significant fraction of its remaining fuel in a single event could be catastrophic. Star formation in that region would effectively be snuffed out, put on hold for millions of years until fresh gas could slowly be accreted from the cosmic filaments, or until the ejected material cooled and fell back in. In this capacity, the first supernova were ruthless cosmic regulators, imposing a limit on how quickly and efficiently a small galaxy could grow by violently expelling the very stuff it needed to build. Yet, in a beautiful and counterintuitive twist, these same explosions could also become powerful agents of creation. While the inner blast wave was vaporizing and dispersing gas, the outer layers of the expanding supernova remnant could act like a cosmic snowplow. As it moved outward, it would sweep up a shell of cooler, denser gas from the interstellar medium, compressing it into a cold, dense layer that was riddled with complex structure and turbulence. Within this compressed shell, gravity could suddenly get a much stronger grip. Local overdensities within the shell could become unstable and begin to collapse, triggering a new, secondary wave of star formation right on the blast wave's leading edge. This process, known as triggered star formation, means a single dying star could be responsible for the birth of dozens or even hundreds of new stars. It's a stellar version of a phoenix rising from the ashes, where death directly begets new life. The key factor determining whether a supernova was a net destroyer or a net creator likely came down to the environment. In a very small, low-mass protogalaxy with weak gravity, the explosive energy would dominate, easily blowing the gas away and quenching further activity. But in a slightly larger, denser, or more clustered environment, the surrounding gas might be too massive to be completely dispersed. There, the compressive effects of the shockwave could win out, leading to a burst of new stellar births and actually accelerating the galaxy's development. Quantifying this balance is the heart of the modern mystery. How many supernovae did it take to permanently sterilize a small protogalaxy? How often did their shockwaves successfully trigger a new generation of stars? The answers depend on details we are still trying to pin down, such as the precise masses of the first stars and the typical density of the gas clouds in which they formed. A pair instability supernova, which utterly obliterates its star, would inject far more energy and spread its metals more widely than a core collapse supernova that leaves a black hole remnant. The former might be far more effective at shutting down star formation on a local scale, while the latter might allow for a more gentle, productive enrichment. Astronomers use incredibly complex computer simulations to model these ancient fireworks, trying to recreate the conditions of these first explosions and watch how the virtual gas responds. They seed simulated dark matter halos with virtual stars of different masses, set off supernova, and then watch for millions of years of simulated time to see if the galaxy's star formation rate plummets or spikes. The results are rarely clear-cut. They show a delicate and chaotic interplay, where the same event can be destructive in one part of the cloud and creatively triggering in another. This feedback loop, established by the very first stars, set a pattern that would govern galaxy evolution for billions of years to come. It created a self-regulating cycle where star formation itself produces the explosions that can later halt or encourage further star formation. The first supernovae were the universe's first and most powerful lesson in cause and effect, teaching the cosmos that creation is often inextricably linked with destruction. Their legacy is written into the very demographics of the stars we see today, in the chemical patterns of the oldest stellar fossils, and in the fundamental fact that not all of the primordial gas was instantly turned into stars. By both clearing out and compressing the cosmic gas, these titanic blasts ensured that the story of galaxy formation would be one of fits and starts, of booms and busts, ultimately creating a more diverse and interesting universe than if it had been a simple, steady process of assembly. Imagine a star, but not one powered by the searing nuclear fusion we understand. Envision instead a celestial object that glows with the heat of an entirely different kind of physics, a star fueled by the self-annihilation of dark matter. This is the incredible premise behind one of the most exotic ideas in modern cosmology, the theoretical existence of dark stars. In the earliest epochs of the universe, when dark matter was far denser and more concentrated within the first protogalaxies, conditions might have been just right for these bizarre objects to form. The process would begin much like a normal population 3-star, with a massive cloud of hydrogen and helium collapsing under gravity. But deep within its core, something extraordinary would happen. As the dark matter particles, pulled in by the star's own gravity, became densely packed, they would begin to collide and annihilate each other, converting their mass directly into a tremendous amount of energy according to Einstein's famous equation. This energy, released as heat and light, would provide a powerful outward pressure, halting the gravitational collapse before the core could ever become hot and dense enough to ignite nuclear fusion. The star would be born, shining brilliantly, but with a dark heart. The properties of such a dark star would be utterly alien compared to anything in the present-day universe. Because the energy from dark matter annihilation can be distributed throughout the star's vast interior rather than being concentrated in a tiny, frantic core, these objects could grow to truly monstrous proportions. Theoretical models suggest they could balloon to sizes millions of times greater than our Sun, with masses reaching up to 1 million solar masses or more. Their sheer physical size would be almost incomprehensible. If one were placed at the center of our solar system, its surface would extend far beyond the orbit of Earth, engulfing the inner planets. And unlike their fusion-powered cousins which live fast and die young, dark stars could have enjoyed remarkably long lifetimes. As long as there was a sufficient supply of dark matter particles in the core to fuel the annihilation process, the star could remain stable for millions, or even hundreds of millions of years, shining with a steady, powerful glow that would make them beacons in the early cosmic dark. This leads to the tantalizing possibility that the James Webb Space Telescope might have already seen one. When astronomers point Webb at the most distant, ancient galaxies, they are looking for faint, red points of light. A dark star would present a very specific and unusual signature. It would be an incredibly massive, extended object emitting a continuous spectrum of light, rather than the specific absorption lines we typically associate with stars. Its immense size would also make its surface temperature relatively cool, causing it to glow with a reddish hue. Some of the very faint, red, and puzzlingly large objects that Webb has detected in its deep field surveys could, in fact, be these primordial dark stars masquerading as early galaxies. Distinguishing a dark star from a small cluster of normal stars is an enormous challenge, but it's a challenge astronomers are now actively undertaking by analyzing the precise details of the light these objects emit. The discovery of even a single confirmed dark star would be a watershed moment for science, creating a profound and direct bridge between the two greatest mysteries in modern physics: the nature of dark matter and the formation of the first cosmic structures. It would provide the first direct evidence that dark matter is not just a passive gravitational scaffold, but an active, interactive substance that can undergo particle processes. By studying a dark star, we could potentially learn about the mass of dark matter particles, their interaction cross-sections, and their distribution in the early universe, information that is completely inaccessible through any other means. These objects represent a breathtaking convergence of the very large and the very small, where the rules of particle physics dictate the evolution of the largest structures in the cosmos. They stand as a powerful reminder that the infant universe may have been host to phenomena far stranger and more wonderful than we have yet dared to imagine, and that the first starlight might have been born from the annihilation of the darkness itself. Orbiting our Milky Way like ancient, glittering swarms are the globular clusters, dense, spherical collections of hundreds of thousands of stars, all bound together by gravity in a volume so tight that the core would be a sky ablaze with neighboring suns. These celestial relics are among the oldest objects we can study. Many are over 13 billion years old, forming when the universe itself was in its infancy. Their mere existence presents a fascinating timing problem. How did such massive, gravitationally bound structures, which have survived virtually unchanged for almost the entire history of the cosmos, assemble themselves so quickly and so early? Their formation requires pulling together a vast amount of gas, converting it into stars with incredible efficiency, and then having that entire stellar city remain stable for billions of years. Unraveling their origin is like finding a perfectly preserved prehistoric city. It gives us a direct window into the construction methods of the young universe, a time when the rules of galactic assembly were being written. One of the leading theories suggests these clusters are the surviving cores of ancient dwarf galaxies that were torn apart and devoured by larger galaxies like our own. In the hierarchical model of galaxy formation, the Milky Way grew by consuming countless smaller protogalaxies. During this violent process, the fragile outer stars of a dwarf galaxy could be easily stripped away by tidal forces, leaving behind only its dense, resilient core. This core, already a compact cluster of stars, would then continue to orbit as an independent entity, a globular cluster. The evidence for this is compelling. The largest globular cluster in the Milky Way, Omega Centauri, has several characteristics that set it apart. It contains multiple generations of stars with a spread of ages and chemical compositions, which is more typical of a dwarf galaxy than a single, simple star cluster. It also has a distinct, massive central region, leading many astronomers to conclude that we are not looking at a cluster at all, but at the leftover nucleus of a small galaxy that was almost entirely digested by the Milky Way long ago. This scenario paints a picture of the early universe as a demolition derby, where the densest and toughest structures are the only ones that survive intact. However, not all globular clusters fit this dramatic narrative. Many others show a stunningly pure and simple stellar population, with all their stars appearing to have the same age and chemical composition. This suggests they formed in a single, rapid, and intense burst of star formation from a single, collapsing cloud of gas. So how could a cloud collapse so completely without fragmenting into many smaller clusters or forming a more complex, galaxy-like structure? The answer likely lies in the unique conditions of the early cosmos. The gas that formed the first globular clusters was probably extremely dense and under immense external pressure, perhaps at the turbulent intersection of colliding streams of gas within a growing protogalaxy. In these high-pressure environments, the collapse is so fast and furious that star formation can reach efficiencies of 50% or more, meaning half of all the available gas is converted into stars almost instantly. This is in stark contrast to modern galaxies, where the efficiency is a meager 1 or 2%. This incredibly productive burst would create a huge mass of stars in a very small volume, resulting in a gravitational bond so strong that it could withstand billions of years of tidal forces and encounters with other structures. This leads to a captivating mystery. Were the first globular clusters the very first galaxies? It's a provocative question. Some of the faintest, most ancient galaxies now being discovered by the James Webb Space Telescope bear a striking resemblance to what we would expect a newborn globular cluster to look like. They are small, incredibly dense, and are undergoing a ferocious burst of star formation. The distinction between a small, independent galaxy and a globular cluster destined to orbit a larger one might have been very blurry in the beginning. Perhaps the very first structures to light up were these ultra-dense stellar factories. Whether they remained as independent ultra-compact dwarfs, or were later captured by larger galaxies to become the globular clusters we see today, would have depended entirely on their surroundings and their luck in the cosmic lottery of mergers. This idea positions globular clusters not as mere byproducts of galaxy formation, but as potential pioneers, the universe's first successful experiment in building large, stable stellar systems. Their incredible longevity is a testament to the success of that initial design, a blueprint for stellar communities that has endured since the dawn of time. Amidst the grand narrative of gravitational collapse and stellar explosions, there's a subtle but potentially powerful force we haven't yet considered, one that weaves an invisible web through the cosmos, influencing everything from the smallest gas cloud to the largest galactic disk. This is the mysterious role of magnetic fields in the early universe. Today, we can detect magnetic fields almost everywhere we look. They are threaded through galaxies. They permeate the vast spaces between them, and they even shape the winds of newborn stars. But in the very beginning, was the universe born with these magnetic fields, or did it have to generate them from scratch? This question might seem esoteric, but the answer could reshape our understanding of how the first structures emerged from the smooth, featureless aftermath of the Big Bang. The central debate revolves around the origin of these so-called seed fields. One compelling possibility is that they are truly primordial, imprinted onto the fabric of space-time during the universe's earliest moments, perhaps during a period of rapid inflation. In this scenario, quantum fluctuations could have been stretched to cosmic scales, creating unimaginably weak magnetic fields that were present from the very first instant. These fields would have been absurdly faint, billions of times weaker than the Earth's own magnetic field, but they would have been everywhere, a fundamental part of the cosmic landscape from day one. The alternative theory suggests a more dynamic birth. Instead of being a relic of creation, magnetic fields may have been forged by the first astrophysical processes. The violent turbulence in the first protogalaxies, the powerful jets from the earliest black holes, or the colossal shock waves from the first supernova could have acted like a cosmic dynamo, twisting and amplifying any tiny, random magnetic irregularities into organized, large-scale fields. It's the difference between the universe being born with a faint, universal whisper of magnetism, or learning to generate its own magnetic voice through its first chaotic acts of creation. So, why does this distinction matter? Because even a seemingly insignificant magnetic field can have an outsized impact on the behavior of gas, the primary building block of stars and galaxies. In the modern universe, magnetic fields play a crucial role in supporting gas clouds against their own gravity, regulating how they collapse, and even driving powerful outflows from young stars. In the primordial cosmos, their influence, though subtle, could have been a decisive factor. For instance, magnetic fields can create a form of pressure that acts like a gentle, invisible scaffold within a collapsing cloud of hydrogen. This support can slow down the collapse, giving the gas more time to cool and fragment. This might have prevented the formation of a single, monstrous star, and instead encouraged the birth of a small, multiple star system. In this way, the presence of even a weak magnetic field could have directly influenced the initial mass function of the very first stars, perhaps making the fabled 100 solar mass giants slightly rarer and allowing for more smaller stars to form alongside them. Furthermore, magnetic fields are master controllers of cosmic, raise the high-energy protons and atomic nuclei that race through space at nearly the speed of light. The first supernova would have been prodigious accelerators of these particles, creating fierce winds of radiation that battered the surrounding gas. Magnetic fields act as cages for these cosmic rays, trapping them and guiding their propagation. A stronger, more organized primordial field would have confined these energetic particles closer to their source, concentrating their energy and potentially heating the local gas, which could suppress further star formation. A weaker, more disorganized field would have allowed the cosmic rays to diffuse more freely, spreading their energy over a larger volume and creating a more uniform, warmer background. This delicate interplay between magnetism, cosmic rays, and gas temperature represents a complex feedback loop that we are only just beginning to model with supercomputers. A loop that would have dictated the pacing and efficiency of how the first galaxies built themselves. The hunt for evidence is incredibly challenging, but not impossible. Astronomers are searching for the fossil record of these early magnetic fields imprinted on the light from the most distant quasars. As light from these brilliant beacons travels through the intergalactic medium, the polarization of the light, the specific direction in which its waves vibrate, can be subtly twisted by any magnetic fields it passes through. By analyzing the polarization of light from objects at different distances, we can effectively look back in time and probe the strength and structure of magnetic fields at different cosmic epochs. Another clue lies in the oldest stars in our own galaxy. The chemical elements we see in their atmospheres were forged in early supernova, and then transported through magnetized space before being incorporated into new stars. The specific patterns of these elements might yet hold a faint signature of the magnetic fields that guided their journey. Unlocking the mystery of the first magnetic fields is like discovering the invisible rules of a game we've only ever seen the outcome of. It forces us to consider that the cosmos was not just shaped by gravity and radiation, but also by this subtle, pervasive force that directed the flow of matter, moderated the birth of stars, and ultimately helped write the hidden rules of cosmic evolution. So if the first galaxies appeared surprisingly early, that forces us to confront an even broader chronological puzzle. How did the entire timeline of galactic assembly actually unfold? We are essentially trying to reconstruct the universe's own biography, to piece together the precise sequence of events from the first tiny protogalaxies to the vast cosmic cities we see today. For decades, the prevailing view was a more gradualist one, a story of slow and steady growth. In this picture, the first small clumps of stars took hundreds of millions of years to merge and build up into larger structures, with star formation ramping up gradually to a peak around 3 to 4 billion years after the Big Bang. It was a cosmic narrative of patient, bottom-up construction. But the latest observations, particularly those from the James Webb Space Telescope, are tearing that comfortable timeline to shreds. We are now seeing compelling evidence that massive galaxies were already in place when the universe was only a few 100 million years old. A discovery that suggests a frantic, almost explosive period of early assembly that our best models struggle to explain. The central question astronomers are trying to answer is about the universe's overall rise time, how quickly it went from darkness to a state of vibrant stellar activity. Did most of the stars in the universe form in a single, glorious burst of early activity? A cosmic baby boom that lit up the cosmos in a brilliant flash? Or has star formation been a more steady, sustained process over the last 13 billion years, a slow and constant simmer rather than a rapid boil? The answer to this question is fundamental because it dictates how we understand the efficiency of the early universe. A rapid rise time implies that the physical conditions in those first gas clouds were incredibly conducive to star formation, perhaps far more so than they are today. It suggests that gravity worked with breathtaking speed, that gas cooled and collapsed with unprecedented efficiency, and that the first billion years were a period of unrivaled cosmic productivity. A slower, more gradual rise time, on the other hand, would paint a picture of a more hesitant universe, one where star formation was a difficult process to get started, hampered by feedback from the first supernova and the challenges of pulling together material across vast distances. This is where the James Webb Space Telescope has truly turned cosmology on its head. Before Webb, our view of the very early universe was fuzzy and incomplete. The Hubble Space Telescope could see back to a certain point, but the most distant galaxies were just faint red smudges, and their numbers seemed to thin out the further back we looked, fitting the gradual assembly story. Webb, with its infrared eyes, has pierced through that veil, and what it has found is astonishing. Instead of a sparse scattering of infant galaxies, its deep field images reveal a universe that is already teeming with bright, massive, and surprisingly structured galaxies at astonishingly early times. We are finding galaxies that appear to be as massive as our own Milky Way at a time when the universe was only 3 or 4% of its current age. It's the equivalent of looking at a photo of a human kindergarten class and finding several children who are already 6 feet tall and have full-time jobs. The data is forcing a massive recalibration of our models. To understand why this is so revolutionary, you have to appreciate what the simulations predicted. Cosmological simulations are like virtual universes that scientists run on the world's most powerful supercomputers. They take our best understanding of the laws of physics, gravity, gas dynamics, dark matter behavior, and let them play out from the Big Bang forward. For years, these simulations have been incredibly successful at reproducing the large-scale structure of the universe we see around us today. But when astronomers input the new Webb observations, these same virtual universes consistently fail to produce enough big, bright galaxies so early on. The simulated early universe looks anemic and underdeveloped compared to the real one Webb is showing us. This discrepancy is not a minor tweak. It's a fundamental tension that points to something crucial missing from our physics. Perhaps star formation in dense, primordial gas was exponentially more efficient than we thought. Maybe the first stars really did form in those exotic supermassive clusters we discussed earlier, creating dazzling brightness with less total mass. Or it could be that the dark matter halos formed earlier and were more massive than our cold dark matter paradigm allows. This new evidence for a dramatically sped-up timeline has profound implications. If massive galaxies assembled much faster than we thought, it means the universe reached a state of maturity and complexity breathtakingly quickly. The period known as the cosmic dawn wasn't a long, slow sunrise. It was a sudden flash of daylight. This changes how we think about the subsequent evolution of galaxies. A galaxy that forms its core of stars in a violent, concentrated burst in the first 500 million years will have a very different life story than one that assembles its mass gradually over billions of years. Its stellar populations will age together, its chemical enrichment will happen rapidly, and it might exhaust its gas supply much sooner, leading to an early transition into a passive, red and dead elliptical galaxy. This frantic early pace might also help explain the rapid growth of supermassive black holes, as they would have had massive, gas-rich galaxies to feed from right from the very beginning. We are being forced to rewrite the opening chapters of the cosmic story, replacing a tale of gentle awakening with one of a sudden and brilliant cosmic revolution. When we picture a galaxy, we often conjure an image of a majestic spiral, like Andromeda or our own Milky Way, with its elegant arms sweeping around a bright core, or a smooth, fuzzy elliptical galaxy, a vast cloud of ancient stars. We assume these classic forms are the result of billions of years of serene evolution. But when we point the James Webb Space Telescope to the edge of the observable universe, we are getting our first clear, high-definition glimpse of what galaxies looked like in their infancy, and the picture is far more chaotic and diverse than anyone predicted. The emerging mystery is one of morphology, the study of form and structure. Why did some of these infant systems already show hints of organized disks, while others were nothing but clumpy, irregular blobs? The shapes we are now seeing in the early cosmos are a direct window into the physical processes that governed their chaotic youth, and ultimately set them on their lifelong evolutionary paths toward becoming the familiar galaxy types we recognize today. The first surprise from Webb's data is the sheer prevalence of what astronomers call clumpy irregulars. A vast number of the most distant galaxies look nothing like the symmetrical spirals and ellipticals nearby. Instead, they resemble scattered, glowing splotches, like handfuls of glitter thrown onto black velvet. They are often elongated, stringy, or appear as a series of 3 or 4 brilliant, disconnected knots of light embedded in a faint, common haze. These bright knots are not individual stars. Each one is a massive, dense stellar nursery, a region where star formation is occurring at a ferocious, unsustainable rate. A single one of these clumps could be forming stars so intensely that it outshines the rest of the galaxy combined. This clumpy structure is a telltale sign of a system in its raw, turbulent youth. The galaxy is essentially a container of frantic stellar birth, with gravity pulling the gas into these dense, unstable pockets that ignite with starlight before they have a chance to settle into a more orderly configuration. The galaxy is being built from the inside out in a series of brilliant, localized firestorms. This leads to a compelling question. What physical processes dictated whether an infant galaxy would be one of these chaotic blobs, or begin to show signs of a more serene, organized disk? The answer lies in a delicate cosmic tug-of-war between 3 powerful forces: the frantic pace of internal star formation, the violence of galactic mergers, and the gentle, steady rain of fresh gas from the cosmic web. In the clumpy irregulars, star formation is the dominant sculptor. When a galaxy is forming stars at an explosive rate, the energy output is immense. The fierce ultraviolet radiation and powerful stellar winds from massive stars can blow holes in the surrounding gas, stirring it up and preventing it from settling into a calm, rotating disk. The galaxy exists in a state of constant, energetic feedback, where each new generation of stars violently rearranges the very gas that will form the next generation. It's a self-perpetuating cycle of chaos, where the engine of creation is also the primary source of disorder. Yet, amidst this cosmic bedlam, Webb has also spotted a significant number of surprisingly structured galaxies at remarkably early times. We are now seeing faint but distinct red disks, galaxies that already exhibit a central bulge and a thin, rotating plane of gas and stars when the universe was less than 1 billion years old. This discovery is just as baffling as the irregulars. How could a galaxy settle down so quickly? The secret to forming a stable disk is a gentle, ordered supply of cold gas. Picture a galaxy not being built by violent collisions, but by quietly sipping cool, pristine hydrogen from the vast, filamentary rivers of the cosmic web. When gas flows into a galaxy in a smooth, steady stream along a consistent direction, it can carry a lot of rotational energy. This gas naturally settles into a spinning disk, much like how spinning pizza dough flattens out into a wide, regular circle. For a disk to survive, however, the galaxy must avoid major mergers. A significant collision with another galaxy of similar size is like throwing a rock into that spinning pizza dough. It completely destroys the delicate order, randomizing stellar orbits and puffing the galaxy up into a more spheroidal, elliptical shape. So, the presence of an early disk galaxy is a cosmic sign that it has lived a relatively sheltered life, growing peacefully through steady accretion while its more chaotic neighbors were being battered by violent encounters. This brings us to the grand evolutionary puzzle. How do these initial infant shapes connect to the galaxy types that dominate the universe today? The prevailing theory is that the clumpy irregulars are the likely precursors to modern spiral galaxies. Over hundreds of millions of years, the dynamics within a clumpy galaxy naturally lead to a more ordered structure. The brilliant, massive clumps of stars exert a strong gravitational pull on the surrounding gas and on each other. Through a process called dynamical friction, these dense clunks slowly lose energy and migrate inward, eventually merging to form the central bulge of a galaxy. Meanwhile, the remaining gas, no longer being stirred up by such intense, localized starbursts, can finally settle into a more stable, rotating disk, where star formation becomes a more orderly process, tracing out the iconic spiral arms we see today. Our own Milky Way's thick disk and central bulge may very well be the fossilized remains of a wild, clumpy youth that calmed down over billions of years. On the other hand, the path to becoming an elliptical galaxy is a far more violent and transformative one. Ellipticals are the cosmic retirement homes for stars' vast, roundish collections of old, red stars with very little gas or ongoing star formation. They are not born this way. They are made through a series of major galactic mergers. When two disk galaxies of roughly equal size collide, it is a truly catastrophic event. Their delicate structures are completely shredded. The orderly rotational motion of the stars is converted into random, chaotic orbits, creating a blurry, spheroidal shape without any discernible disk. Furthermore, the collision funnels a colossal amount of gas into the central regions, triggering an incredible burst of star formation that can use up the entire galactic gas supply in one final, extravagant firestorm. The shockwaves from the merger and the intense radiation from newly formed stars can also heat or blow away any remaining gas, leaving the galaxy unable to form new stars. It becomes red and dead, a massive elliptical whose future is one of gradual fading. The morphology of a galaxy is therefore a permanent record of its most traumatic life events. A smooth elliptical is a galaxy that survived a cosmic car crash, while a grand spiral is one that enjoyed a more peaceful and orderly upbringing. The James Webb Space Telescope is acting as the ultimate cosmic historian, allowing us to take a galactic census across billions of years. By counting the fractions of disks, irregulars, and spheroidal systems at different cosmic epochs, we can finally map out this evolutionary sequence in real time. We can watch as the population of chaotic, clumpy blobs decreases over cosmic time, while the fraction of well-ordered disks and puffed-up ellipticals increases. Every new deep field image is another data point in this grand story of transformation. The incredible diversity of shapes we see in the infant universe is a direct reflection of the varied and often violent conditions of the cosmic dawn. Some galaxies were forged in the calm, steady flow of intergalactic gas, while others were sculpted by the hammer blows of catastrophic collisions. This fundamental link between a galaxy's present-day form and its ancient history is one of the most profound narratives in all of cosmology, revealing that the majestic spirals and serene ellipticals we admire today are the living descendants of a wild and tumultuous youth. Now, let's connect this grand story of cosmic origins directly to our own existence by exploring one of the most profound and speculative mysteries of all. Could the very first stars have been surrounded by planets? And if so, what bizarre worlds would they have been? It's a staggering thought. The possibility of worlds orbiting those primordial, titanic suns. On the surface, the idea seems impossible. We know that rocky planets like Earth are built from heavy elements: silicon for rock, iron for cores, carbon for the chemistry of life. Yet, the first population, 3 stars, were born from purely pristine gas, containing not a single atom of these crucial ingredients. They were metal-free by definition, so where would the material for planets even come from? The answer lies in the spectacular, self-sacrificing deaths of these same stars. While the stars themselves were pure, their cataclysmic supernova explosions were the universe's first and most productive heavy element factories. In their final moments, these giants forged a first wave of carbon, oxygen, silicon, and iron, and then blasted it out into the surrounding cosmic environment. This is where the magic of dust comes in. As the expanding supernova remnant expands and cools, these newly minted heavy elements can begin to clump together, forming microscopic solid particles, the first dust grains in the cosmos. Think of it as the universe's first snowfall of soot and sand, condensing right out of the fiery aftermath of a stellar explosion. So, while the protoplanetary disk around a living population, 3-star would have been devoid of dust, the environment around its corpse would have become suddenly and dramatically enriched. If a second generation of stars began to form from this polluted gas cloud, a cloud now seeded with these pristine, first-generation heavy elements, then those new stars could potentially have been born with the necessary ingredients for planet formation already swirling around them. The timeline for this is incredibly tight. A massive population 3-star lives and dies in just a few million years. If the shockwave from its death triggered the collapse of a nearby gas cloud, the next stellar nursery could have ignited remarkably quickly, with its protoplanetary disk containing the very dust grains forged in the recent explosion. This opens a fascinating, though narrow, window for the first possible planets to emerge around these early second-generation stars. So, if such worlds did form, what would they have been like? They would have been utterly alien, nothing like the diverse planets we find in our modern galaxy. For one, they would have been exceptionally metal-poor. There would be no vast continental plates of granite, no deep mantles of rich minerals. The available rocky material would have been a primitive, basic blend of simple oxides and carbides. You might get a small, rocky core, but it would likely be a barren, geologically dead world, devoid of the plate tectonics that recycle planetary crusts and regulate atmospheres on Earth. Any atmosphere such a world managed to hold onto would have been a bizarre, primitive concoction. With little oxygen or nitrogen available, it might have been composed primarily of hydrogen and helium leftover from the star's formation. A thick, primordial haze that would create crushing pressures and a permanent, deep greenhouse effect, more similar to a mini-Neptune than to Earth. And this leads to the most tantalizing, spine-tingling question of all. In such an extreme and ancient environment, could life have ever gained a foothold? The chances are infinitesimally small, but from a purely chemical perspective, the building blocks were present. The supernova of the first stars produced carbon, the essential backbone of organic chemistry. They also produced oxygen, which could combine with hydrogen to form water. So, the absolute fundamental ingredients for life as we know it, carbon-based chemistry and liquid water, were present in the universe for the first time ever. If a carbon-rich, water-bearing planet could form in the habitable zone of a stable, long-lived second-generation star, then the prebiotic conditions for life might theoretically have existed. This pushes back the potential dawn of life in the cosmos from billions of years after the Big Bang to just a few 100 million years. A truly revolutionary thought. Of course, the environment would have been incredibly hostile. The early universe was a much more violent place, with a higher density of massive stars going supernova nearby, bathing any fledgling world in intense doses of ultraviolet and X-ray radiation. Without a protective ozone layer or a strong magnetic field, such a planet would have been constantly sterilized from above. Furthermore, the extreme rarity of heavy elements means that the sheer abundance of the key nutrients required for biochemistry would have been millions of times scarcer than on Earth. It would be like trying to build a complex metropolis with only a handful of scattered pebbles. While the chemistry might have been possible, the path to the organized, complex structures of life would have been exponentially more difficult. Yet, the mere possibility is what captivates the imagination. If life did, against all odds, emerge in such a primordial era, it would have had a multi-billion-year head start on the evolution of intelligence compared to us. While it remains a highly speculative and remote possibility, this mystery forces us to confront a humbling and awe-inspiring idea. We may not be early arrivals in the story of cosmic life, but rather latecomers to a universe that may have been experimenting with biology since its wild and explosive youth. But to truly appreciate the dawn, we must first understand the profound depth of the night that preceded it, a period so vast and silent it's almost impossible to fathom. This was the cosmic Dark Ages, a chapter in our universe's history that stretched for about 100 million years. A long, cold night between the fading embers of the Big Bang and the first spark of a star. Imagine a sky with no points of light, no sun, no moon, no faint, hazy band of a distant galaxy. Just an unbroken, absolute, and profound blackness in every direction you could possibly look. This was the reality of the cosmos for millions upon millions of years. The only source of illumination was the cosmic microwave background radiation. But by this time, it had cooled and stretched from a blinding, visible glow into invisible microwaves and radio waves. To any hypothetical eyes, the universe was a perfect, impenetrable vault of darkness. It was a cosmos in waiting, a vast stage set with all the raw materials, but with the main actors yet to step into the spotlight. The Dark Ages began as the universe expanded and cooled enough for the free electrons and atomic nuclei, which had been bouncing radiation around in a hot, opaque fog, to finally combine and form neutral hydrogen atoms. This event, known as recombination, cleared the cosmic fog and made the universe transparent for the very first time. The light from that event is what we now detect as the CMB, our baby picture of the cosmos. But once that light was released, a profound silence fell. The universe was now filled with this neutral hydrogen gas, and for a while nothing happened. It was a simple, quiet, and almost boring place. The seeds of future structure were there, the tiny density fluctuations imprinted on the CMB, but they were still far too small for gravity to get a proper grip. The universe was like a vast, dark ocean, with only the faintest of ripples on its surface, waiting for a storm to stir it up. The central mystery of this epoch is pinpointing the exact moment this long night finally ended. When did the very first luminous object ignite? We know it happened, but we don't know precisely when, or what that object even was. Was it a single, solitary population, 3-star, blazing to life in an otherwise empty void? Or did several of them ignite in quick succession within a small protogalaxy? This moment, the cosmic equivalent of a single match being struck in a cavernous dark room, is one of the most sought-after events in all of astronomy. The problem is, it's incredibly difficult to observe directly. The neutral hydrogen gas that filled the universe during the Dark Ages acts as a kind of cosmic blotting paper, absorbing the most direct light from these first sources, particularly a specific wavelength of ultraviolet light called Lyman-alpha. So, the very first starlight is, in a way, hidden from us, absorbed by the same medium it was trying to illuminate. So, how do we probe this era? Astronomers use clever, indirect methods. One is to look for the shadows and the echoes. As the first stars and galaxies began to turn on, their intense ultraviolet radiation started to heat the surrounding hydrogen gas. This heating would have caused a subtle shift in the way the gas interacts with the background radio waves from the CMB. By using giant radio telescopes to map the sky at very long, low-frequency wavelengths, projects like the Square Kilometre Array are hoping to create a three-dimensional map of the hydrogen gas during the Dark Ages and the subsequent dawn. They are looking for the telltale signatures of patches of gas that were being heated by the first sources of light. It's like trying to map a dark forest by listening for the echoes of the first few voices that break the silence. Another approach is to push our telescopes to their absolute limits to find the very farthest, and therefore the very earliest, galaxies we can. The James Webb Space Telescope is at the forefront of this effort. By staring deeply at patches of sky for days on end, it gathers the incredibly faint, reddened light from galaxies whose light has been traveling for over 13 billion years. Finding a galaxy that existed just 200 million years after the Big Bang is getting us incredibly close to the actual end of the Dark Ages. But there's a fundamental challenge. We cannot see the very first star or the very first galaxy with our current technology. It is simply too faint, too small, and its light is too heavily absorbed by the intervening hydrogen. The end of the Dark Ages wasn't a single, sudden event you could point a telescope at and witness. It was a transition, a gradual process where isolated points of light began to flicker on, one by one, across the cosmic map, each one burning a small hole in the pervasive darkness until their collective glow finally overwhelmed the night and ushered in the brilliant cosmic dawn we now inhabit. Yet, to truly witness the dawn, we need more than just the faint, distant light of the earliest galaxies. We need to hear the universe's own voice, a whisper from the silent Dark Ages themselves. This brings us to a profound and technically dazzling mystery: the hunt for the 21-centimeter signal from neutral hydrogen. This isn't light in the way we normally think of it. It's a faint radio hum emitted by the most abundant substance in the early cosmos, the lone hydrogen atom. Every single neutral hydrogen atom in the universe is like a tiny, natural radio transmitter, and it broadcasts on a very specific, predictable wavelength, 21 centimeters. This signal is a direct thermometer and a map maker for the infant universe, a tool that could allow us to create a three-dimensional movie of the cosmos as it transitioned from darkness to light. The power of this signal lies in its ability to tell us about the state and temperature of the gas. During the deep, cold, dark ages, the neutral hydrogen gas would have been emitting this 21-centimeter signal, but it would appear in absorption against the even brighter background of the cosmic microwave radiation. This is because the gas was colder than the background glow. Then, as the first stars and black holes began to heat the gas with their radiation, that relationship would have flipped. The warmed hydrogen would then begin to emit the 21-centimeter signal brightly, showing up in emission against the background. By carefully tuning our radio telescopes to this specific frequency, and then measuring how it changes across the sky and at different redshifts, we could effectively slice through cosmic time. We could watch as the first brilliant bubbles of ionization grew and overlapped, mapping the precise progress of reionization in a way that no other observation can. It would be the ultimate cosmic documentary, showing us the universe's transformation frame by frame. The monumental challenge, however, is that this primordial whisper is incredibly faint, and it's buried under an avalanche of cosmic noise. The signal we're trying to detect has been traveling for over 13 billion years, and in that time, the expansion of the universe has stretched its wavelength from 21 centimeters to several meters. This places it in the low-frequency radio band, a part of the spectrum that is notoriously polluted by human-made interference, everything from television broadcasts and satellite transmissions to our own cell phones. But even if we could launch our telescopes into the most remote regions of space, we would still face an even greater problem: our own galaxy. The Milky Way blazes with synchrotron radiation at these same radio frequencies, a foreground emission that is millions of times brighter than the faint signal from the early universe. Trying to find the 21-centimeter signal is like trying to hear a single, quiet conversation in a crowded sports stadium while a jet engine is roaring overhead. The technical feat required is almost beyond comprehension. This is where heroic, global projects like the Square Kilometre Array enter the story. This isn't a single telescope dish. It's a vast, coordinated network of thousands of radio antennas being built across the remote deserts of South Africa and the outback of Western Australia. By combining the signals from all these widely separated antennas, the SKA acts as a single, colossal radio telescope with a collecting area of, you guessed it, over 1 square kilometer. Its primary mission in this field is to perform this ultimate cosmic archaeology, to filter out the deafening foreground static of our own galaxy and the modern world. and to isolate that pristine, ancient whisper from the neutral hydrogen of the cosmic dawn. The data processing required is mind-boggling, involving some of the most sophisticated supercomputer algorithms ever developed, all designed to subtract everything we know about the local radio sky in the hope of revealing the subtle, underlying pattern from the dawn of time. Successfully detecting this signal would be nothing short of a revolution in cosmology. It would provide us with a direct, unedited snapshot of the universe during its most formative epoch, a baby picture far more detailed than the single, static image provided by the cosmic microwave background. We would see the first structures beginning to ripple the cosmic gas, long before they ever collapsed into stars. We could directly identify the locations and the timing of the very first ionizing sources, settling the debate about whether stars or black holes were the primary drivers of reionization. It would be the ultimate validation, or refutation, of our entire theoretical framework for the early universe. The 21-centimeter signal is the universe's own diary of its childhood, and we are now, for the first time, developing the technology to carefully open its pages and read the story written there. A story that holds the key to understanding how our vibrant, structured cosmos emerged from the silent, simple emptiness of the beginning. To understand how the grand tapestry of galaxies was woven, we must journey back to a time before time, to the very first fraction of a second after the Big Bang. This was the epoch of cosmic inflation, a period of exponentially rapid expansion where the universe ballooned from a subatomic speck to a volume larger than our entire observable cosmos in less than a blink of an eye. It sounds like the wildest science fiction, but it's a cornerstone of modern cosmology, and its fingerprints are believed to be all around us, encoded in the very distribution of galaxies. The central mystery here is profound. How do we connect the physics of this unimaginably brief, energetic instant directly to the majestic galactic cities that emerged hundreds of millions of years later? The answer lies in the ghostly hand of quantum mechanics, which provided the raw blueprint for all of creation. In the seething, energetic frenzy of the inflationary field that drove this expansion, the universe was not perfectly smooth. According to quantum theory, empty space is never truly empty. It's a bubbling cauldron of virtual particles constantly flickering in and out of existence. These are quantum fluctuations, tiny, random variations in energy that appear and disappear so quickly we normally never notice them. But during inflation, something extraordinary happened. The expansion of space was so incredibly fast that these minuscule quantum ripples were stretched along with it, frozen into the fabric of space-time and magnified from the quantum realm to cosmic proportions. Imagine the surface of a perfectly smooth balloon. Now, imagine a microscopic grain of sand resting on it. As you inflate the balloon to the size of a house, that tiny grain becomes a significant macroscopic bump. Inflation did exactly this to the universe, taking quantum whispers and amplifying them into the gravitational seeds for everything to come. These stretched fluctuations were imprinted as tiny differences in the density of matter and energy across the newborn cosmos. Some regions were ever so slightly denser than others. After inflation ended, the universe was filled with this subtle, patterned canvas. Gravity, being an attractive force, then got to work. Over the ensuing eons, it began to preferentially pull matter into those slightly denser regions. More matter meant stronger gravity, which pulled in even more matter, in a powerful feedback loop that turned microscopic seeds into colossal structures. The densest knots grew into the first dark matter halos, which then gathered gas, ignited stars, and became the protogalaxies that would eventually merge into the galaxies we see today. So, in a very real sense, the vast cosmic web of galaxies, with its great clusters and immense voids, is a direct, blown-up map of the quantum jitters that existed when the universe was less than a trillionth of a second old. The incredible evidence for this story is written across the sky in the oldest light we can see, The cosmic microwave background. The CMB is a snapshot of the universe when it was just 380,000 years old, and it is not perfectly uniform. It is modeled with tiny temperature variations, hotter and colder spots that differ by only a few millionths of a degree. These minute fluctuations are the direct descendants of those primordial density variations laid down by inflation. They are the fossilized imprint of the gravitational potential wells that would later guide the formation of structure. The pattern of these spots, their size, their distribution, their statistical properties, matches the predictions of the inflationary model with stunning accuracy. It tells us that the initial conditions for galaxy formation were indeed set by a period of rapid, quantum-driven expansion. Yet, the mystery is far from solved. The central question now is not whether inflation happened, but how it happened. What was the specific nature of the inflationary field? What were its exact properties? Different models of inflation predict subtle but crucial differences in the pattern of those initial fluctuations. Some models would produce a Gaussian random field, meaning the fluctuations are perfectly random, while others might predict specific kinds of non-Gaussianity, tiny correlations between fluctuations of different sizes. Some models predict a universe with primordial gravitational waves, ripples in spacetime that would leave a distinct polarized pattern, called B modes on the CMB. Detecting or ruling out these signals is the key to understanding the physics that operated at energy scales a trillion times higher than anything we can achieve in our particle accelerators. This is where the distribution of galaxies themselves becomes our most powerful tool. While the CMB gives us a two-dimensional baby picture, the three-dimensional map of galaxies across cosmic time shows us how those initial seeds actually grew up. By conducting massive galaxy surveys, like the Sloan Digital Sky Survey or the future Euclid and Nancy Grace Roman Space Telescope missions, astronomers are creating a cosmic census of unprecedented scale. They are measuring the precise positions and distances of millions of galaxies, allowing them to reconstruct the large-scale structure of the universe. The statistical clustering of these galaxies, how they group together on different scales, holds within it the encoded memory of the initial inflationary spectrum. It's a cosmic fossil hunt, where the fossils are entire galactic systems. By comparing the observed clustering of galaxies with predictions from different inflationary models, we can work backwards, testing which model of the universe's explosive birth best matches the grand architecture we inhabit today. The quest to understand inflation is therefore a dual one, combining the search for the faintest whispers in the ancient light of the CMB with the monumental task of mapping the modern cosmic web. All to read the opening sentence of the universe's story, a sentence written in the language of quantum gravity. This brings us to a deeply contemplative puzzle, one that asks what became of those pioneering island universes. After the frantic construction of the cosmic dawn, what was the ultimate destiny of the very first galaxies? The story our simulations tell is one of relentless, large-scale violence. In the hierarchical model of cosmic growth, the early universe was a chaotic, competitive environment where bigger structures consistently consumed smaller ones. Many of those first, fragile protogalaxies, with their few million stars, were likely drawn into the gravitational pull of larger, growing neighbors. They were shredded by tidal forces, their stars stripped away and incorporated into the halos of the giants we see today, like our Milky Way. The process is a form of galactic cannibalism, and it suggests that most of the genuine first generation no longer exist as independent entities. Their stellar populations are now the ancient, metal-poor stars that form the sparse halo surrounding our galactic disk, the dispersed archaeological evidence of a long-forgotten act of cosmic consumption. Yet, the possibility remains that not all of them met this dramatic end. Could some of these primordial galaxies have escaped this fate, surviving in isolated pockets of the cosmos as true living fossils? The idea is compelling. For a galaxy to remain pristine and unchanged for over 13 billion years, it would need to have led an incredibly sheltered life. It would have had to form in a region that was largely devoid of nearby neighbors, a quiet backwater of the cosmic web where the gravitational tug of war was minimal. After its initial, rapid burst of star formation used up its available gas, it would have needed no fresh inflows to trigger new generations of stars. It would have become a cosmic dead end, a galaxy that lived its entire life in a single, brilliant flash and then simply faded, its stellar population aging in lockstep into a quiet red glow. Finding such an object would be like discovering a lost world, a secluded valley where the biological and geological rules of a bygone era have been perfectly preserved. The hunt for these relic galaxies is a major astronomical endeavor, and it has led to the identification of some fascinating candidates. One of the most famous is a small, nearby galaxy known as I-Zwicky 18. For a long time, it was thought to be a truly newborn galaxy, because its stars appeared to be extremely young, and it was undergoing a violent starburst. Upon closer inspection, however, astronomers discovered that it also contains a much older population of stars. It seems that this galaxy managed to retain a large reservoir of pristine gas for billions of years, only recently beginning to form stars again. It is not a perfect fossil, but it demonstrates that some galaxies can indeed remain dormant and unevolved for astonishingly long periods. More promising candidates are certain ultra-faint dwarf galaxies orbiting the Milky Way. These systems contain only a few thousand stars and are so dim they were only discovered in the last 2 decades. Their stars are incredibly old and metal-poor, suggesting they formed almost all their stars in a single, initial burst and have done virtually nothing since. They are the closest things we have to untouched relics from the cosmic dawn, frozen in time by their own minuscule gravity and lack of interaction. The value of finding a perfect, pristine example cannot be overstated. It would serve as a pristine laboratory, an unspoiled control sample against which we could test all our theories about the early universe. By studying its stellar populations in exquisite detail, we could determine the exact initial mass function of the very first stars within it. We could measure the chemical abundances in its gas, which would reflect the yield from the very first supernova without any later pollution. Its structure would reveal the original dynamics of galaxy assembly, unaffected by the violent mergers that reshaped most other systems. It would be a direct portal back to the era of the first galaxies, offering a clear, unambiguous view of the universe's initial conditions for structure formation. The quest to find this astronomical Rosetta Stone continues to drive deep sky surveys as astronomers sift through the faintest, reddest objects in the sky, hoping to find that one perfect time capsule that has, against all odds, preserved the dawn of galactic life in perfect, undisturbed detail. Now, as we piece together the grand structure of our cosmic neighborhood, we stumble upon a glaring discrepancy, a conflict between our most sophisticated theories and the actual census of the sky. This is the missing satellite problem, and it strikes at the very heart of our understanding of dark matter and the rules of cosmic assembly. Our lambda cold dark matter model, the reigning champion of cosmology, is incredibly successful at predicting the large-scale structure of the universe. When we run supercomputer simulations of how dark matter should clump under gravity, starting from the initial conditions of the Big Bang, they produce a beautiful, hierarchical cosmic web. Crucially, these virtual universes show that large galaxies like our Milky Way shouldn't exist in isolation. They should be surrounded by a vast, swirling retinue of thousands of smaller dark matter halos, the invisible scaffolds upon which small dwarf galaxies could form. It's a prediction that seems robust and logical, a direct outcome of the bottom-up model of structure formation. But when we step away from the computer screen and actually look up at the night sky, the numbers don't add up. The Milky Way's entourage is far more modest, To date, we have only confirmed about 60 satellite dwarf galaxies orbiting our home. That's a huge gap, a chasm, really between the thousands predicted and the few dozen observed. It's as if a detailed architectural blueprint for a bustling metropolis called for hundreds of small shops and cafes on every block. But when you arrive, you find only a handful of scattered, tiny stalls. This isn't just a minor accounting error. It represents a fundamental mismatch between our theoretical expectations and the observed reality of our local universe. The question is stark. Are the missing satellites truly absent, or are they just hiding in plain sight? And what does their apparent absence tell us about the laws that govern the cosmos? One compelling line of thought suggests the problem isn't with the theory, but with our own observational limitations. Perhaps the vast majority of those predicted dark matter halos are indeed out there, but they are simply too faint for us to see. They could be what astronomers call dark galaxies, halos that either never managed to attract enough gas to form stars, or had their gas stripped away early on. Or they could host a stellar population so sparse and dim that they effectively vanish against the background glow of the night sky. The recent revolution in this field has come from massive digital sky surveys, which use automated telescopes to scan the heavens and then powerful algorithms to search for these ultra-faint dwarfs. This technique has already borne fruit, more than doubling the number of known Milky Way satellites in the last decade alone. Many of these new discoveries are so faint that they contain fewer stars than some globular clusters, yet they are spread over a much larger area of space, making their surface brightness incredibly low. It's entirely plausible that thousands more of these ghostly, star-poor halos are still lurking in the darkness, waiting for the next generation of even more sensitive telescopes to finally reveal them. However, another possibility is far more radical. The problem might not be with our eyes, but with our theory. Perhaps our understanding of dark matter itself needs a fundamental revision. The standard model assumes dark matter is cold and collisionless, meaning its particles only interact through gravity. But what if dark matter has other, subtler properties? If dark matter were slightly warm, meaning its particles were lighter and faster moving, it would have profound consequences. Warm dark matter particles would have enough energy to stream away from the very smallest gravitational potentials, effectively smoothing out and erasing the tiniest density fluctuations. In a warm dark matter universe, there would be a distinct lower limit to the size of the first structures to form. The thousands of tiny halos predicted by the cold dark matter model would simply never get a chance to coalesce. Instead, the first halos to form would be larger, and their number would be significantly reduced, potentially bringing the theoretical predictions much more in line with the dozens of satellites we actually see. The missing satellite problem, therefore, becomes a powerful experimental test, using the galaxy we call home as a laboratory to probe the fundamental nature of the universe's most mysterious substance. There's a third, equally fascinating angle that involves the complex physics of star formation itself. Let's assume all those small dark matter halos do exist. The question then becomes, why didn't they all light up with stars? The early universe was a much more hostile place, bathed in the intense ultraviolet radiation from the first galaxies. This background radiation could have heated the gas in the smallest halos, preventing it from cooling and collapsing to form stars. It's like trying to build a snowman on a warm day. The material is there, but the conditions won't allow it to stick together. Furthermore, even if a few stars did manage to form, the first supernova explosion in such a tiny galaxy could have been catastrophic. The relatively shallow gravitational well of a small dwarf galaxy would have been unable to hold onto its gas against the violent blast. A single supernova could have blown the entire galactic gas reservoir clear out into intergalactic space, permanently quenching star formation and leaving behind a dark, starless halo. In this scenario, Our census of luminous satellites is not a count of all the halos, but only of the rare, lucky ones that were either massive enough to withstand these early trials, or that formed their stars late enough to avoid the most turbulent era. The missing satellite problem forces us to consider not just gravity, but the intricate and often destructive interplay between gas, radiation, and feedback in the smallest cosmic systems. It reminds us that the universe is not just a collection of matter, but a dynamic system where the rules of physics play out in a dramatic and consequential battle between creation and destruction. Imagine a galaxy that spans the same vast distance across space as our own Milky Way, a structure that could contain hundreds of billions of stars. Now, picture that same colossal volume of space, but instead of being filled with a brilliant, swirling disk of suns, it holds only 1% of the stellar population. Its few stars scattered so sparsely that the entire galaxy becomes almost transparent, a ghostly cobweb of light against the black velvet of the cosmos. This is not a theoretical phantom. It is a real and puzzling class of objects known as ultra-diffuse galaxies, or UDG, and their very existence challenges our basic assumptions about how galaxies are built and how they endure through time. How can something so large possess so little substance? And what does the survival of these cosmic will owe? The WISPs tell us about the hidden rules governing galactic life and death. The story of their discovery is a testament to how much we still have to learn about our own cosmic backyard. For decades, these galaxies remained hidden in plain sight. Their surface brightness was so incredibly low that they simply melted into the background glow of the night sky. It took increasingly sensitive digital surveys and meticulous processing to finally tease their faint, smeared-out signals from the data. Some of the most famous examples, like the hauntingly beautiful dragonfly 44 in the Coma cluster, were found not in isolated voids, but in the most crowded and violent neighborhoods imaginable dense galaxy clusters. This location makes their survival all the more miraculous. Galaxy clusters are cosmic mosh pits, filled with hot, tenuous gas and dominated by fierce gravitational tides. For a galaxy as fragile as an UDG to exist in such a brutal environment is like finding a delicate, intricate soap bubble floating completely unscathed in the heart of a hurricane. It forces us to ask whether these structures are incredibly resilient, or if they are being actively protected by something we cannot see. This leads directly to the central enigma of their formation. How does a galaxy grow to such an immense size without ever forming a proportional number of stars? Astronomers are investigating several compelling, and sometimes conflicting, origin stories. One prominent theory suggests that UDGs are failed spiral galaxies. In this scenario, a normal protogalaxy, with all the potential to become a grand spiral like the Milky Way, begins to form in the early universe. It accumulates a massive halo of dark matter and gathers a large reservoir of gas. But then, something goes wrong. Perhaps it falls into a dense cluster too early, and the intense pressure from the surrounding hot intergalactic medium acts like a cosmic blowtorch, stripping away its gas before it can convert most of it into stars. Or maybe fierce feedback from its own early supernova was so effective that it blew out the star-forming fuel, permanently quenching its own growth. The galaxy is left with the expansive skeleton of a giant, but with only a tiny smattering of stellar inhabitants. A second, more radical idea posits that ultra-diffuse galaxies are not failed giants at all, but rather puffy dwarfs. Their enormous apparent size in this view is an illusion created by their unique dark matter halos. Perhaps these galaxies formed within halos that have an unusually high angular momentum, causing them to spin rapidly. This high spin would naturally fling stars and gas out into a much more extended, diffuse configuration without requiring a massive total weight. Alternatively, their dark matter halos might possess a uniquely chord profile, with a much shallower gravitational well in the center compared to the steeply rising cusps predicted by standard cold dark matter models. This softer gravitational potential would allow stars to orbit further out, again creating a large, spread-out galaxy from a relatively modest amount of mass. Distinguishing between the failed giant and the puffy dwarf model is one of the most active areas of research, as it directly tests our understanding of the fundamental connection between dark matter and luminous matter. The plot thickens considerably when we consider their potential connection to the ancient universe. Could some of these ultra-diffuse galaxies be genuine living fossils, pristine relics from the cosmic dawn that have somehow persisted for billions of years? This is a tantalizing possibility. A UDG that formed in a quiet, isolated void might have used up its initial gas supply in a single, rapid burst of star formation. Without any subsequent mergers or fresh inflows of gas to trigger new activity, it would have simply shut down, its stellar population aging in unison into a quiet, red glow. It would be a galactic time capsule, preserving the conditions of the early universe in its stellar compositions and its structure. Finding such an object would be the astronomical equivalent of discovering a secluded island where dinosaurs still roam, offering an unobstructed view into a bygone era of cosmic evolution. However, observations reveal that UDGs are not a monolithic class. Some, particularly those in clusters, are indeed old and quiescent, full of ancient red stars. But others, found in quieter group environments or in isolation, show signs of ongoing star formation and even reservoirs of neutral hydrogen gas. This diversity implies that there is no single pathway to becoming an ultra-diffuse galaxy. The universe seems to have multiple recipes for creating these faint giants. Some are the battered survivors of a violent cluster environment. Others are the quiet, reclusive hermits of cosmic voids. And still others might be the product of unique galactic interactions, like tidal forces that stretch a smaller galaxy into a diffuse stream. Their very existence in all their varied forms forces us to broaden our definition of what a galaxy can be. They demonstrate that size and brightness are not always linked, and that the most common structures in the cosmos might be these faint, ghostly giants, waiting patiently in the darkness for us to develop the tools to see them. But to truly complete the reionization story, we have to shift our gaze from the brilliant beacons to the cosmic collective, to the possibility that the real work was done not by a few spectacular giants, but by an uncountable number of faint, whispering dwarfs. This is the captivating mystery of the faint galaxy population. The idea that the universe's great reawakening was a grassroots movement, powered by the combined light of billions of tiny, humble galaxies that were, until very recently, completely invisible to us. We've been like someone trying to understand a city's power grid by only studying the spotlight on a stadium, completely missing the combined glow from every single household light bulb across the entire metropolis. The combined ultraviolet output from this vast, unseen population could have been the steady, pervasive background radiation that finally burned away the last vestiges of the primordial fog. The case for these faint dwarfs as the primary agents of reionization is surprisingly strong. While a single massive galaxy or a brilliant quasar produces a staggering number of ionizing photons, these objects were likely rare in the early universe. More importantly, their intense radiation often creates powerful feedback, blowing bubbles around themselves but also potentially heating up the gas on larger scales and making it harder for smaller galaxies to form. Faint, low-mass galaxies, on the other hand, could have been incredibly numerous. The fundamental predictions of the cold dark matter model suggest that the cosmos should be teeming with small dark matter halos, each one a potential host for a tiny, star-forming dwarf. Because these systems have much shallower gravitational wells, their feedback is less destructive. A supernova might blow out a significant fraction of their gas, but it's less likely to completely sterilize the galaxy or heat the intergalactic medium over vast distances. This means they could have provided a more gentle, widespread, and sustained source of ionizing radiation. a soft ultraviolet hum that permeated the cosmos for hundreds of millions of years. The central puzzle, and the reason this remains a wide-open question, is a matter of sheer numbers. To provide enough total ionizing power, the early universe would have needed an astonishing abundance of these faint systems, far more than we were able to see with previous telescopes like Hubble. For decades, our deep field images showed a gradual decline in the number of galaxies the further back we looked. A trend that seemed to suggest there simply weren't enough small galaxies to get the reionization job done. This missing population became a major problem, forcing theorists to rely more heavily on the exotic and rare population, 3 stars or early black holes, to explain the lifting of the fog. The question was stark. Was our theory of small structure formation wrong, or were our telescopes just not powerful enough to see the true cosmic population? This is precisely where the James Webb Space Telescope has plunged into the debate with breathtaking results. Webb was explicitly designed to find these faint, high redshift dwarfs, and it is not disappointing. Its deep field images are not just showing us the brilliant, massive galaxies we expected. They are revealing a background tapestry of countless faint, red smudges, each one a tiny, distant galaxy previously lost in the noise. Early analyses suggest the number of these ultra-faint galaxies could be 10 times higher, or even more, than what Hubble could detect at the same cosmic distances. We are suddenly seeing the supporting cast of the cosmic dawn, and it is a cast of billions. This discovery is fundamentally rewiring our understanding of the early universe's demographics. It suggests that the initial stellar mass function in these small halos might have been skewed toward producing more bright, massive stars than we see today. Or that star formation in dense primordial gas was simply far more efficient on these small scales. The universe, it seems, was much better at making small, faint galaxies than we ever imagined. However, detecting them is only the first step. The monumental challenge now is to measure their total contribution to the reionization budget. We need to know not just how many there are, but how many ionizing photons they are actually producing, and most critically, how many of those photons are escaping into intergalactic space. This last part is the real wild card. In the modern universe, most galaxies are terrible at leaking their ionizing radiation. The ultraviolet light that can rip electrons from hydrogen is easily absorbed by the dense clouds of gas and dust within the galaxy itself. For a galaxy to be an effective reionization engine, it needs to have clear, unobstructed channels for this hard radiation to escape. We call this the escape fraction, and for reionization to work, the average escape fraction across all these early galaxies needed to be surprisingly high, perhaps 10 or 20%. How did these small, fragile systems achieve this? Perhaps their low mass and weak gravity made it easier for supernova to punch holes in their gas clouds, creating clear tunnels for the radiation to pour out. Maybe their low metallicity meant they had less dust to absorb the light, making them more transparent to their own intense glow. JWST is now using its spectroscopic capabilities to hunt for the direct signature of escaping Lyman-alpha and Lyman continuum radiation from these early dwarfs, a measurement that is crucial for turning a galaxy count into a definitive answer for their role in cosmic history. The implications of this mystery stretch to the very nature of galaxy formation itself. If the faint galaxies truly dominated reionization, it means that the smallest structures were not just passive bystanders in the early cosmos. They were the primary drivers of its most important transformation. It suggests that the key to understanding the universe's transition from darkness to light lies in the physics of low-mass halos, in the complex interplay between gas accretion, star formation, and feedback on the very smallest scales. It also provides a beautiful, holistic picture of cosmic evolution, where the same countless tiny building blocks that hierarchically assembled into giant galaxies like our Milky Way were also responsible for cleaning and preparing the intergalactic medium for that very assembly to occur. The quest to finally solve the reionization puzzle is no longer just about finding a few brilliant culprits. It is about taking a full census of the cosmic population and understanding how every single member, no matter how faint, contributed to the collective effort of ending the universal dark age and illuminating the cosmos for all that was to come. And so we arrive at the final, and perhaps most profound, question in our journey: the ultimate fate of the very first stars. We've followed them from their birth in pristine clouds to their spectacular deaths that seeded the cosmos. But what was their final end? Did every single one meet a cataclysmic demise, or could some have slipped quietly into the night, leaving behind secrets that might still be found today? The answer is far from simple, branching into multiple possibilities that hinge on one critical factor: mass. For the true titans of the first generation, those behemoths born with masses above 250 times that of our Sun, the end was swift and absolute. Their own gravity was so overwhelmingly powerful that after exhausting their nuclear fuel, no force in the universe could prevent their total collapse. There was no dramatic supernova explosion to mark their passing. Instead, the entire star would have imploded, vanishing directly into a black hole without a final flash of light. It's a strangely silent and eerie demise for such a brilliant object, a cosmic giant simply winking out of existence, leaving behind only a gravitational pit in spacetime as its legacy. For the slightly less massive, yet still enormous, population, 3 stars, those between roughly 80 and 250 solar masses, the end was the universe's most powerful firework, the pair instability supernova. As we've discussed, these stars were completely obliterated, torn apart from the inside out in a blast so energetic it temporarily outshone entire infant galaxies. This was a sterilizing, self-destructive end that left no remnant behind, scattering its unique chemical signature across the cosmos. But this leads to a captivating and unresolved puzzle. Our models suggest that the first generation of stars wasn't a monolithic group of only giants. While the initial mass function is thought to have been top-heavy, favoring very massive stars, there is a compelling possibility that a lower mass tail also existed. What about the smaller population 3 stars, those that might have formed with masses similar to, or even less than, our own Sun? These stars would have had a completely different life story. Without heavy elements in their cores to act as catalysts, their nuclear fusion would have proceeded at a slower, more steady pace. Crucially, a star with the mass of our Sun, but composed only of hydrogen and helium, could have a lifespan stretching not for billions but for trillions of years. This is in timescale so vast that it exceeds the current age of the universe by 1,000-fold. This stunning possibility opens up one of the most thrilling hunts in modern astronomy: the search for a surviving population 3 star. Imagine finding a stellar fossil, a pristine relic from the cosmic dawn that has been shining quietly in some forgotten corner of the cosmos for the last 13 billion years. It would be the astronomical equivalent of finding a living dinosaur wandering a remote jungle, a direct, unaltered window into the conditions of the primordial universe. Such a discovery would be transformative. By analyzing the atmosphere of this star, we could finally know, with absolute certainty, the chemical composition of the gas from which the first stars formed. We could test every single prediction about population 3 stars, from their internal structure to their nuclear burning processes, against a real, observable object. It would instantly validate or refute decades of theoretical work, making it one of the most significant discoveries in the history of science. So, where would we even begin to look for such a ghost? The most promising hunting grounds are the halos of large galaxies like our own Milky Way. The galactic halo is a vast, spherical cloud of ancient stars and dark matter that envelops the main disk. It's essentially the archaeological dig site of our galaxy, containing the shredded remains of the very first dwarf galaxies that merged to build the Milky Way. Within this sparse population of ancient stars, there could be a few genuine, untouched survivors from the first generation. Astronomers are systematically surveying the sky, using powerful telescopes to take detailed spectra of the most metal-poor stars we can find. The current record holders, stars like SMSS J0313, are incredibly ancient and metal-poor, but they are not perfect. They still contain a tiny, trace amount of iron, proving they are second-generation stars, formed from gas polluted by a single prior supernova. The Holy Grail is a star with zero detectable metals, a star whose spectrum shows only the pure lines of hydrogen and helium, with no sign of carbon, oxygen, or iron whatsoever. The search is painstaking, requiring us to sift through millions of stellar spectra to find that one, perfect, primordial needle in a cosmic haystack. The existence of even a single such star would confirm that pockets of perfectly pristine gas persisted long enough for a few last, lonely first-generation stars to form, forever changing our understanding of the timeline of chemical enrichment in the early cosmos. This enduring quest to find a living messenger from the dawn of time ensures that the story of population, 3 stars, is not just a tale of the distant past, but an ongoing detective story, one whose most exciting chapter may yet be written. From the profound silence of the cosmic dark ages to the frantic assembly of the first galactic cities, the journey to uncover the mysteries of the first stars and galaxies is nothing less than the ultimate detective story. We have ventured across 30 profound frontiers, each one a testament to the sheer ingenuity of the human spirit and our relentless drive to understand our place in the cosmos. We have stood in awe of ghostly population, 3 stars, whose brilliant but fleeting lives set the entire cosmic cycle in motion. We have wrestled with the enigmatic births of the first black holes, debating whether they were born as stellar corpses or as direct collapse giants. We have mapped the great reionization of the universe, trying to identify the primary architects who burned away the primordial fog and made the cosmos transparent. And we have been humbled by the realization that the very atoms that make up our bodies were forged in the hearts of those long-vanished stellar titans, connecting our own origin story directly to the dawn of time. Each of these puzzles, from the nature of dark matter to the peculiar shapes of infant galaxies, represents a vibrant and active frontier of human knowledge, a place where our fundamental theories are constantly being tested, challenged, and refined. We are living in a truly golden age of discovery, a moment in history where our tools are finally catching up to our ambitions. The James Webb Space Telescope is not just another instrument. It is a time machine, peering back to an era we once thought was forever lost to observation. Its unprecedented infrared vision is already upending our timelines, revealing galaxies that are too massive, too bright, and too structured to exist so soon after the Big Bang, forcing a thrilling re-evaluation of our most cherished cosmological models. Groundbreaking radio arrays like the Square Kilometre Array are preparing to listen for the faint whisper of neutral hydrogen from the cosmic dawn, promising to give us a dynamic movie of the universe's transformation from darkness to light. Meanwhile, increasingly sophisticated computer simulations are creating virtual universes in silico, allowing us to test out these wild ideas about star formation, feedback, and galactic assembly in a cosmic laboratory. We are no longer merely speculating about the first stars. We are gathering the forensic evidence, piece by piece, from the chemical fossils in our galactic backyard to the faint red smudges at the edge of the observable universe. We stand on the cusp of breakthroughs that could, within our lifetimes, solve enigmas that have persisted for generations, finally bringing the cosmic dawn into sharp focus. This grand quest is far more than an academic exercise. It is a deeply human one, rooted in our innate curiosity and our desire to know where we came from. The story of the first stars is, in a very real sense, our own origin story. Every time you feel the warmth of the sun on your skin, you are feeling the energy of a star that would not exist if the first generation had not manufactured the heavy elements that made its formation possible. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of it was created in the nuclear furnaces of stars that lived and died long before our sun was even a glimmer in a nebula. We are not just living in the universe. We are the universe made from its stardust, brought to life by its physical laws, and now gifted with the consciousness to look back and wonder at its magnificent history. To explore the cosmic dawn is to explore our own deepest ancestry, tracing our lineage back to the very first moments when the universe began to build complex structures out of simplicity. As we bring this exploration to a close, we want to turn the question over to you. The night sky is a shared human heritage, a canvas for our collective imagination and curiosity. So, we invite you to look up. The next clear night you have, take a moment to step outside and simply gaze at the stars. Consider that the light from many of them has been traveling for thousands of years to reach your eyes, and that each one is a part of this ongoing, epic story of cosmic evolution. Think about the incredible journey from the first spark of light to the majestic spiral of our Milky Way, and the unlikely chain of events that led to you being here, right now, to contemplate it all. We would love to hear which of these 30 mysteries captured your imagination the most. Was it the ghostly hunt for a living population 3-star? The dramatic self-destruction of a pair instability supernova? Or perhaps the mind-bending possibility of dark stars, glowing with the heat of annihilating dark matter? Share your thoughts in the comments below, and let us know what you find most fascinating about our universe's wild and mysterious infancy. The conversation is just beginning, and every new perspective adds to our shared sense of wonder. Stay